Okay, hi there, Dr. Matthew J. Trom here. We are in a new chapter of the book, chapter 7, and hence a new module, convective heat transfer for external flow. And this is lecture 13, external flow over flat plates. The lecture corresponds to section 7.1, 7.2, and 7.3 in the book. If you are watching this video in summer 2026, you might be worried that we've skipped a number here between the previous lecture and this one. We are just doing them in the opposite order. So don't worry that you missed anything. When we get the chapter 6 stuff finished, that will be posted, and we'll have a lecture 12 that'll correspond to that. But we haven't done that yet. So we're doing things a little out of order. If you are looking for the ADA compliant transcription, this is the video that will generate that transcription. And so when I get the transcription from Zoom, I will put the link here, and you'll be able to click on the PowerPoint slide link and get to the transcription if you are looking for it. Okay. So let me get my laser pointer going. There we go. All right. So dating myself a little bit here, but in 2026 summer, one of the blockbuster movies that came out was The Odyssey, starring Matt Damon as Odysseus. And this is kind of a funny meme that's related to that movie that came through my social media feed, which is in order to prepare for the scene in the Odyssey where he screams in anguish, trying to resist the call of the sirens, Matt Damon was forced to derive the Navier-Stokes equations in spherical coordinates, right? And here's at least one of three Navier-Stokes equations in spherical coordinates. And here's cute Matt Damon, and here's Matt Damon screaming in anguish as he's deriving them. So the reason that I put this meme up, it's a fluids meme, not a heat transfer meme, but the reason that heat transfer requires fluids as a prerequisite is because there's an enormous amount of fluids. You basically have to solve a fluids problem before you can solve a heat transfer problem in convection. And so this is just a reminder of that relationship between fluids and heat transfer and your love of the Navier-Stokes equations. All right. The book is kind of weird in that it actually goes through the entire solution and then goes back and says, this is what I was doing as I was solving the problem. I think that makes very little sense pedagogically. And so I'm going to describe to you how to solve these problems in this 10 point list. And then I'll actually, go through how to do it. So I think that makes more sense. So first thing that we're going to do in this 10-step process whenever you encounter a convection problem is to repeat silently to yourself that all the action is in the boundary layer, right? Now, this is a little bit of a joke, but if you took fluids with me, basically everything that happens in the boundary layer with respect to fluids problems. And so for heat transfer problems, that's even more important. And so anytime you tackle any of these problems, you really need to put all of your focus in the boundary layer and solve both fluids problems and heat transfer problems, or fluid equations and heat transfer equations in the boundary layer for all these different geometries. So this is just a reminder to focus your attention on the boundary layer. Next thing we're going to do is identify the flow geometry. So we've got flow over flat plates, spheres, cylinders, all kinds of weird shapes. You need to be able to figure out what the geometry is in order to tell you which direction to go with selection of your correlations. Next, you're going to specify the reference temperature. I have a slide on this. Typically, the reference temperature is called a film temperature. It's the average of the temperature of the object that's undergoing heat transfer and then the free stream temperature, but sometimes not. So we'll dig into that a little bit more. One of the really important outcomes from what we're going to talk about today is the underlying equation for convective heat transfer in a boundary layer is also the underlying equation for mass transfer, right? So when I say mass transfer, I mean like the diffusion of particles in a gas. So like humidity, for example, water vapor and air. And so even though this is a heat transfer class, it turns out that we basically get, 2 for 1. So one solution for free, which is if you solve the heat transfer problem, you're also inadvertently getting the solution to the mass transfer problem. And so in this chapter, we talk a little bit about mass transfer. And so if you happen to be solving a mass transfer problem instead of a heat transfer problem, the reference temperature is the the fluid properties at the temperature of species B, where species B is the background gas through which the gas that you're interested or the particles that you're interested in are diffusing. So, for example, if you've got water vapor diffusing in air, water vapor is species A and air is species B. So, for specifically mass transfer problems, you're going to determine the fluid properties at the temperature of species B, whatever that is, the background gas. Um, for heat transfer problems, you're going to evaluate the pertinent fluid properties at the reference temperature, whatever that may be. So now you have a series of fluid properties, things like Prandtl number, things like thermal conductivity. Those are all tabulated based on temperature, and you're going to find those values in the appropriate tables for whatever the reference temperature was that you specified in step 2 for heat transfer, or sorry, step 3 for heat transfer, or step 4 for mass transfer. Once you've got all those properties, now you've got enough to calculate the Reynolds number. You will calculate the Reynolds number every single time you solve one of these problems. So important to know the flow geometry and the properties so you can choose the right Reynolds number and plug in the properties appropriately. Once you have the Reynolds number, then you can determine whether the flow is laminar or turbulent, right? So the flow structure. Once you've got all of those pieces, then you have to decide whether the problem is asking you for a local heat transfer or a surface average heat transfer. If it's local, there's a particular set of correlations. If it's average, there's a different set of correlations. So you need to combine all these pieces of information to figure out what correlation to pick. Ultimately, we get to step 9, which is like the culmination of kind of this treasure hunt to find all of this information that gets you to this spot. So when you get here, you're going to select the appropriate correlation. There's 2 types of correlations. Nusselt number correlations are for heat transfer, and Sherwood number correlations are for mass transfer. There is a different correlation for every different combination of geometry, Reynolds number, dimensionless properties, fluid properties, and laminar or turbulent. So you need to have all these things figured out, and then you go and look up the appropriate correlation, which most of them are determined empirically by experiment, but some, particularly those that are flow over a flat plate, are actually determined analytically. So we'll talk through that. So once you pick the appropriate correlation, you're going to plug in the parameters that you found in all the previous steps, and out will pop the appropriate heat or mass transfer coefficient, which you then use in Newton's law of cooling to figure out how much heat got moved for a particular temperature difference. So that's the sequence. There are a number of dimensionless numbers, right? We like to make everything dimensionless. Remember, back to fluids with similarity, because once you solve the problem once, you basically got it solved for every other problem, every other situation that is geometrically similar and it has similar dimensionless numbers. So you only need to run one experiment, and now you have the solution to a whole host of different possible arrangements, so long as they are similar and that they have the same geometry and all the dimensionless numbers can be matched. So we will see how everything gets non-dimensionalized to make all of the equations much, much more useful and basically universally applicable. So we have a bunch of dimensionless numbers, which I just kind of litter here so that you can see them and become familiar with them. You should remember from fluid mechanics, the Reynolds number, which is the free stream velocity times some distance x divided by viscosity. Notice that I'm using kinematic viscosity, not dynamic viscosity. I'm doing that on purpose because instead of having to look up density and kinematic viscosity, you just look up one value here, right? The dynamic viscosity. And so this is Reynolds number for a particular spot X. There's also a Reynolds number sub L. This is for flow over a flat plate where L is the distance to the end of the plate. There's also Reynolds number sub D. Capital D is for external flow. Lowercase d is for internal flow, which we'll get to later. And capital D is the characteristic dimension, usually the diameter of the sphere or the cylinder, or the cylindrical or spherical shape for which you're finding the Reynolds number. We have the Prandtl number, which is a ratio of the viscosity to the thermal diffusivity. We also have something called the Schmidt number for mass transfer. That's the ratio of viscosity to the diffusion coefficient. I should mention DAB. This is a diffusion coefficient, units of meters squared per second. A is the species, the chemical species that you're actually tracking its diffusion. And then B is the background gas through which the diffusion is happening. So if you're worried about water vapor diffusing in air, A is water vapor, B is air. Then we have the Nusselt number, which we talked about briefly before. So Nusselt number is a dimensionless heat transfer coefficient for convection. So Nusselt number sub X is the local Nusselt number at a particular spot X, and the Nusselt number is the ratio of H at that same spot X times X, which is the location of the spot, divided by K, the thermal conductivity of the gas that's supporting the convection process. Notice that the Nusselt number and the Biot number look the same, right? They're both like H times the distance over a thermal conductivity. Difference between Nusselt and Biot is that the Nusselt number, the K value is the thermal conductivity of the gas, and in the Biot number, the K is the thermal conductivity of the solid, right? Because Biot number cares about, and what you're trying to determine is whether there's a thermal gradient internal to a solid object, whereas Nusselt number is trying to tell you how much heat transfer you're getting away from the surface of the solid object into the gas that's surrounding it, right? So even though they look the same, Hx over K, this K for Nusselt number is the gas, and K for the Biot number is the solid. So that's what differentiates them. This again is the local Nusselt number at X. We have a Nusselt number at L, so that's the Nusselt number for an entire plate of length L. I've got a bar over it because it's an average value, right? So you take the local Nusselt number at X and you sum up through an integration all of the different Nusselt numbers all the way along the plate, and then you take the average, and that's Nusselt number with a bar over it. The Nusselt number with a bar over it gives you an average heat transfer coefficient, average convection coefficient, HL bar, which is multiplied by L and divided by K to give you that dimensionless Nusselt number sub L. But this one you would use if you wanted to find the heat transfer for an entire surface, right? You find the average convective heat transfer for the surface, multiplied by the area, multiplied by the temperature difference, and that gives you the heat transfer. This is if you're looking for the heat transfer from a single spot. You just take H for that single spot, multiply by the distance to that spot, divide by K, and that gives you H for that one spot. So that's what this line represents, this bar on the top. It's local versus average. Just like we have a local, or sorry, an average Nusselt number for length over a plate, for flow over a plate, we also have an average Nusselt number for external flow over a cylinder or sphere of characteristic dimension, diameter D, and we end up with H bar D. So this is an average heat transfer coefficient, convective heat transfer coefficient over the surface of a cylinder or sphere. Just like with this one, you multiply this by the wetted area and the temperature difference, and that gives you the total heat transfer for a cylinder or sphere. When we're solving mass transfer problems, instead of Nusselt number, we have a Sherwood number. So this is a local Sherwood number at a particular spot X. It's the ratio of a mass transfer coefficient, convective mass transfer coefficient, so H sub m for mass, at a particular spot X, multiplied by the location of that spot, and then divided by DAB, right? This, again, is the diffusion coefficient of species A and species B. Just like with the Nusselt number, we get an average Sherwood number. So this is the average, dimensionless average mass transfer coefficient over an entire surface. So imagine like a swimming pool, right? So you're taking the average over the entire surface area of the swimming pool. That's this value, multiply by the characteristic length of the swimming pool, divide by the diffusion coefficient of species A and B, and that gives you the Sherwood number. You also can have Sherwood numbers for cylinders and spheres. So Sherwood number bar sub D is the same as Sherwood number bar sub L, except the geometry here is a sphere of character, or a cylinder of characteristic dimension diameter D, as opposed to length L for the flat plate case. Whew. Okay. So we're going to delve into how to get these Nusselt number correlations, which you will then solve for the H value, the force or the external flow convection heat transfer coefficient. And so where do these come from? Well, the good news is if you guys are taking the class in summer 2026, you've already done this. This was lab 3, right? So remember what you did in lab 3 is you basically heated up a aluminum plate and you blew air over that plate at known velocity and some known upstream ambient temperature, right? For you guys, that was setting your thermostat to a particular value or measuring the air temperature in advance. And you knew how much heat we were putting into the flat plate. In this case, it's done by just running electricity through the plate through a resistive heater. You know the current, you know the voltage, so you can come up with the heat that gets deposited into the plate. For us, we use the warm up curve to figure out what that heat transfer rate was. But nonetheless, you know the heat transfer rate. That's ultimately Q. And you know the temperature of the plate, right? And for us, that was taking the thermistor and measuring the temperature of the plate in the thermistor well. And of course, you know the area of the plate, right? Because those are dimensions that were given. So you can then take that given information, prescribe geometry from a heated electrical plate in this case, with known input power, Q dot, maintaining some temperature TS greater than T infinity. I should mention, right, TS is the surface temperature. It does not necessarily need to be greater than T infinity, the ambient temperature. You guys also did a series of experiments where you measured the convection coefficient for a cylinder, right, using the melting cup with ice in it. So that's a situation where TS is less than T infinity. So this works just as well for cooling as it does for heating. But the way that the derivation is done in the book is we assume a heated plate rather than a cooled plate. And so TS is greater than T infinity, at least for this derivation. So you end up with Newton's law of cooling. Here it is, right? So you know Q, you know A, you know TS and T infinity. The only thing you don't know is the convection coefficient. So you can solve this one equation, one unknown for the convection coefficient. That is the average convection coefficient over the entire surface of the plate. And that is the value of import for your correlation. However, you'd like to make this dimensionless so that you can apply it to basically any situation that is geometrically similar and has the same dimensionless numbers. And so we non-dimensionalize that solution, not in terms of velocities and temperatures and heat transfer coefficients, but in terms of Reynolds number, Nusselt number, and Prandtl number, right? All those dimensionless numbers that I described on the previous slide, for a flat plate of characteristic dimension L. And once you've non-dimensionalized in terms of these numbers, you now have a correlation that you can use in other cases where the geometry is similar. Remember, Buckingham pi tells us that there is a relationship between the Nusselt number, the Reynolds number, and the Prandtl number. It tells us that that relationship exists, but it does not tell us what the functional relationship is. So you need to actually run an experiment to come up with that functional relationship to build the correlation. And that's literally what you guys did in lab 3 and what we're going to talk about in this lecture. Okay, so we say here that this procedure is repeated for a variety of test conditions, right? So remember back to Buckingham pi, you want to vary the Reynolds number and the Prandtl number by, for example, changing the velocity, changing for Reynolds number, and then changing the fluid for the Prandtl number, right? Because Prandtl number, if we go back, Prandtl number is viscosity over thermal diffusivity, right? So different fluids or the same fluid at different temperatures will give you different Prandtl numbers. So you're now running experiments by varying these two variables. And that's going to result in a family of resulting Nusselt numbers. And now you can take your Reynolds number, Prandtl number, and Nusselt number and figure out the appropriate correlation by basically plotting them. So it turns out if you plot these experimental values on a log-log plot, what you'll get is a series of lines. Each line is representative of a different Prandtl number. So basically a different fluid, right? Something with a different viscosity, different thermal diffusivity, different Prandtl numbers. But each one of those fluids all of the data for each one of those individual fluids will line up more or less on a straight line, right? There's a little bit of variation because this is an experiment and we expect a little bit of experimental uncertainty, but by and large, you'll get these nice linear relationships between the log of Reynolds number and the log of the Nusselt number. What that means is that there is a power law relationship, right? Because we've got a log-log plot. So power law relationship between the Nusselt number and the Reynolds number. If you wanted to go a step further and say, look, I want to collapse all three of these Prandtl numbers onto a single line, you could do this, right? Which is just taking the Prandtl number and dividing it by the Nusselt number and taking the log of that quotient. And these three separate Prandtl number lines will just collapse onto a single line. And that then gives you a relationship between the Nusselt-Prandtl quotient and the Reynolds number. The slope of this line, because it's a log-log plot, is this exponent m, right? So this exponent here is m, slope of this line. And then c is the intercept, right? So this is a way to get c and m. And then I'll show you later on how you get the exponent for Prandtl number. That's also done experimentally. But you guys have already done this, right? Now, to be fair, you did it for just air at a single temperature. So you did it for a fixed Prandtl number. And so you would have just gotten one of these lines instead of multiple of these lines, but you guys have already done this. You have three experimental data points per person, 15 per team. And in lab 3, I've asked you to take this logarithm of the Nusselt number, logarithm of the Reynolds number, plot those lines, and figure out C and M through linear regression. So this should feel a little bit like a review because you guys have already done this in lab 3. So I say here values of C, M, and M, M and N vary with surface geometry and flow type. So this is true, except this overall correlation is like the correct functional relationship between the Nusselt number, the Reynolds number, and the Prandtl number for all flow over external surfaces, right? So this is true for flow over a flat plate, flow over spheres, flow over cylinders, etc. They all are of this form. So once you get this kind of general form, then it just becomes a matter of how you find C, M, and N for Reynolds number, Prandtl number. Okay, so having then arrived at that correlation using Buckingham pi and some experimental curve fitting, this correlation implies some sort of assumed constant fluid properties. But if you look, so let's just move ahead one slide for a second. If you look, or here, let's go back. Yeah, here, this makes more sense. The surface here is hot at TS, and the free stream is cold at T infinity. And so there's a temperature gradient between the hot surface and the cold fluid. And so the properties, which are functions of temperature, are changing as we move through the fluid. And that would make solving this very, very hard, right? Because you'd have to figure out for each little individual incremental step what the properties did as the temperature changed. And so when experimenters run these tests, there is an underlying assumption that they're going to use constant fluid properties at some universally accepted average temperature, representative temperature. And so when you then use the correlation, if you use that same average temperature and fluid properties for that same average temperature, you end up with the same values using the correlations that were developed experimentally. So we just need to know what the temperature is, right? What the agreed upon protocol is to pick that temperature. So there's two principal ways to do it. The first one, which is the one that's predominantly used in our book, is called the film temperature. So the film temperature is the average temperature between the hot surface and the cold fluid blowing over that surface. So I take TS plus T infinity divided by 2. That gives me the average, which is the film temperature. So normally for these correlations, when you're looking up things like Prandtl number, thermal conductivity, and so forth, viscosity, those numbers are all calculated at this average film temperature. The other way to do it, which is less common, but does exist, and there are a few correlations in our book that do this, so I want you to be aware of it, is to evaluate the correlation at all of the properties associated with T infinity, the free stream temperature. And then you multiply the end result by a temperature correction parameter that accounts for the property variations. This parameter is usually a ratio of Prandtl numbers or sometimes viscosities. So this is the Prandtl number in the free stream versus the Prandtl number associated with the surface, right? Both are temperature dependent. Same is true with the viscosity. And that gets raised to a particular exponent, R. Um, each different fluid has a different R value. So you need to know what the R value is for the fluid that you're using. But ultimately, this is another way of doing it, right? This happens rarely, but it is used. So I want you to be aware that it's there. Um, Okay, so I say here, under conditions where heat and mass transfer are analogous, mass transfer correlation is the same as the heat transfer correlation. So I mentioned this before. Once you've solved the heat transfer problem, you get basically a free bonus, which is the solution to the mass transfer problem. So we have a Nusselt number correlation here, and we have an identical Sherwood correlation here. The only thing that changes is instead of the Prandtl number, we've got the Schmidt number, but these exponents M and N are the same for both of these correlations, and the constant C is the same for both of these correlations. So once you've solved the heat transfer problem, you already have a correlation with all the exponents of the constants for the mass transfer problem. And this is actually a very powerful realization that's used a lot in experimental heat transfer, because it is often easier to measure mass transfer just by like weighing something and seeing how much mass is diffused away from it than it is to measure like, heat transfer or temperatures of, weird shaped objects. And so experimenters will actually build strange geometries that they're interested in finding the heat transfer for out of solids that sublime. So like naphthalene is one of those solids. So solids that sublime in air at ambient conditions, and they'll blow air over these objects, and they'll actually weigh them, periodically to determine how much mass has left. And once you know how much mass is left per unit time, you can work back to find the Sherwood number, and to find these exponents, and then you have the corresponding heat transfer correlation, right, from basically mass transfer experiment. So very, very powerful technique that was used for years and years and years to find heat transfer correlations for complicated geometries where it was impossible to find it any other way. Okay. So there are multiple different geometries that we're going to study in this chapter, but let's start out with flow over a flat plate. If you guys took fluids with me, you know that I got an undergrad degree in aerospace engineering, and so I like flow over flat plates probably much more so than normal mechanical engineers, because flow over flat plates is like the anchoring like knowledge that's required to get things like lift and drag for fixed wing aircraft and lifting bodies. And so I really like this subject because I got my undergrad degree in it. So remember from fluids for flow over a flat plate, um, couple things. First, um, whereas before I described a set of experiments that you would run to come up with empirical correlations, constants for empirical correlations, recall that the flow over a flat plate, for flow over a flat plate, the solution is known, right? This is the Blasius solution for laminar flow over a flat plate. So we do not need empirical correlations, at least not for the laminar part of the flow field, because we've got the exact solution from fluid mechanics. So thank you, Mr. Blasius. The other thing to remember is that for flow over flat plate, there are two different flow regimes, right? So here's our flat plate. It has a characteristic length L. From the leading edge of the plate, we count the distance X, so that's the X direction. And then from the leading edge of the plate upwards, we count Y, so that's the Y direction. And then we have the free stream velocity and temperature. This is air blowing in from the left over the plate to the right. And at least initially, the flow field over the plate is laminar flow, right? So remember, laminar flow, laminar comes from, I think it's the Latin lamellae for layers. So this is well organized, non-chaotic, just flow that basically happens in layers, for which the solution is known, the Blasius solution, as I just mentioned. Um, at some critical Reynolds number called the transition Reynolds number, all of a sudden the flow trips from laminar to turbulent. That's what's shown here. That critical Reynolds number for flow over flat plate is something on the order of about 5 times 10 to the fifth. And it's represented here by X sub C. So this is the critical X value for which the flow transitions from laminar to turbulent. Um, Turbulent flow, totally different animal from laminar flow, right? The fluid is mixing, it's chaotic. And so the heat transfer changes dramatically from this regime to this regime. So we have our plate here. It's heated to a temperature of S, so uniform surface temperature. But in order to find the appropriate heat transfer from this plate into the free stream, we first have to solve the laminar part of the flow field, and then we have to solve the turbulent part of the flow field. So effectively, two different separate problems. And then we have to stitch those solutions together to represent the total heat transfer over this plate that's heated to TS. And, just like I said, with our list, remember our list, repeat silently to yourself, all the action is in the boundary layer. All of the heat transfer associated with flow over flat plate happens in the boundary layer. So the boundary layer on the laminar side grows, and we call the laminator, we call the laminar boundary layer height delta. So delta is growing with X. And then there's also a turbulent boundary layer, which also grows with X, and that's called delta sub T. Those two basically get stitched together at this critical value of X. So we'll get into that when we talk about turbulent flow. For now, we're going to talk about laminar flow, which is why I have boxed the first part of this flow field to remind me to focus on that. So let's zoom down here and remember what the boundary layer looks like. So again, the boundary layer grows from 0 up as you travel down the plate. And its height at any particular spot is called delta. What is the boundary layer? Well, the boundary layer is kind of this arbitrarily decided barrier, if you will, between where the plate has influence on the velocity field and where the plate does not have influence on the velocity field for flow that's headed over the plate. So it's by convention agreed upon that the boundary layer is the spot where the velocity reaches 99% of the free stream velocity. That's just an arbitrary engineering decision. There is in reality no actual physical line in space that you can point to that says this is the boundary layer where things change, right? It's just a subtle difference in the velocity, but that line is basically drawn for the spot where 99% of the velocity of the free stream velocity is achieved, and basically the end of the momentum influence of the presence of the plate. So this is a velocity profile. The no slip condition applies at the base of the plate here, so the velocity has to be 0, and the velocity increases in the boundary layers. You get further and further and further away from the plate, and then when you reach this spot where the velocity is 99% of the free stream velocity, that's the edge of the boundary layer. That influence again grows as you travel down the plate, and delta grows with you. In parallel to the velocity boundary layer, there's also a thermal boundary layer for plates that are heated, like this one that we've been talking about. So the definition is the same, right? So this is the distance away from the plate, characterized as delta sub D. And again, it grows as you travel down the plate. But the distance away from the plate where the temperature of the fluid has reached 99% of the temperature value of the free stream. That's basically the edge of the influence of the plate on the free stream fluid temperature. Same is true, or as is true with the velocity boundary layer. There's something akin to the no slip condition, which is for us, right? You guys have done this before. This is the energy balance between the edge of the solid and the fluid that's touching it. So the temperature of that spot is the temperature of the plate, TS. And in this case, we have a hot plate and cold fluid. And so the temperature is actually going to drop as we get farther and farther away from the plate. So here's my dropping thermal boundary layer. And then once I reach the spot where the temperature is 99% of the free stream temperature, that is the edge of the thermal boundary layer. So these two ideas are analogous. This one velocity boundary layer has to do with momentum transfer, and this one, the thermal boundary layer, has to do with energy, heat transfer um, from the heated plate out into the free stream. Okay, so with that as background, let's jump into fluids a little bit deeper. If you took fluid mechanics with me, you've seen this sequence of slides before. So we're talking about laminar flow over a flat plate. This is the Blasius solution. The way that we got here was before Blasius came along, right? This is 100 years ago, so relatively recent history. Um, Engineers just had to guess at what the shape of the velocity profile looked like. Nobody knew. And so they would, make educated guesses, but nobody knew what the value was. Then Blasius came along, and as we'll walk through here in a second, actually figured out the shape of the velocity profile, which then allowed for an exact solution for the boundary layer growth, the shear at the wall, the skin friction at the surface, and ultimately what we care about from fluids, right? Or for fluids, the drag coefficient, right? Because this is what we use to get the force that this plate experiences as a result of the fluid blowing over it, right? So these are all determined from Blasius's solution. Um, I've got my little exploding man here, my exploding head man. And the reason that's there is because if you've, been an engineer for long enough, you look at numbers like, 0.664 or 1.328, and you say to yourself, that's empirical, right? Somebody ran an experiment to come up with that weird random number, right? It must be experimental. No, no. For the Blasius solution, these numbers that I've circled in green are actually they come from analytical solutions from the known shape of the velocity profile inside the boundary layer. So even though they look empirical, these are exact values, not based on experiment, but based on an actual closed form analytical solution. So to me, that's just super cool. So I always like to point that out. Um, Okay, so let's do a little bit of a refresher into the Blasius solution. We dug way deeper into this in the fluid mechanics class, but just as a refresher so that you know where we're going, remember the great kind of insight that Blasius had is if you look at the velocity profile inside a boundary layer, it turns out that each one of these velocity profiles is a similar shape, meaning that this one and this one are actually identical, except this one to the far right is just stretched in the y direction, whereas this one, is basically shrunken in the y direction. And so it turns out these are all the same velocity profile. They're just stretched by some scaling factor. So that stretching factor, scaling factor is called eta, and that sets the scaling that you need in the y direction at every x location to ensure that each one of these velocity profiles is similar. And so that's like the underlying innovation is that there's this similarity in velocity profiles, and the velocity profiles are all related to each other by a stretching factor. Once you realize that, you can actually then solve for the shape of the velocity profiles inside the boundary layer, which is what Blasius did. Okay, so this is another slide that I use in fluids. In order to get the Blasius solution, you need two things. So one is you need that realization that the velocity profiles along the plate are all the same. They just get scaled. And then two, you have to have a solution that satisfies both the Navier-Stokes equation and the mass conservation equation inside the boundary layer, right? So this is also super cool because as we talked about in fluids, right? Remember back to our screaming Matt Damon, right? The Navier-Stokes equations almost never can be solved, right? There are very few situations for which they can actually be solved to find a closed form analytical solution. It turns out that inside the boundary layer for flow over a flat plate, that's one of the like 5 situations where you can actually get a solution to the differential equation that represents the Navier-Stokes equation. So here it is, right? Not the solution, but the equation itself. And then here's the equation for mass conservation. So we're going to take those two pieces of information. We're going to run them through a pretty intense derivation, and we're going to get the Blasius equation. If you are interested in seeing the derivation, I've got a YouTube video here. It's not my video, but I think this is a pretty rigorous and not too overwhelming video that shows you how to do the derivation. The way that I describe it is we've got our two professors kind of doing their derivation, and there's a step that says, and then a miracle occurs, right? And I think you should be more explicit here in step two, says one professor to the other. So for our purposes, we are engineers. We don't need to know how to do this derivation. But if you're interested in how it's done, I think it's fascinating. There's a YouTube video that you can click on to get to that derivation. The end result is the Blasius equation. So we have some function, and these hyphens are not hyphens. These uh, quotation marks here. This represents a third derivative of this function. This represents a second derivative of the function, and this is the function itself. So the third derivative of f plus 1/2 f times the second derivative of f is equal to 0. That is the solution to Navier-Stokes mass conservation in the boundary layer. And the fact that this solution exists and somebody came up with it has earned, another exploding head from me, because I think this is awesome. Okay, so now we're gonna put all those pieces together. Ooh, and I'm not sure what this weird little thing here. I think it's just an artifact. It's not something that I intended to be there, so I will erase this in the slide deck that I publish. Okay, so we have our Blasius solution. We have our scaling factor eta, right? That tells us how much each one of those velocity profiles has to be stretched for them all to be similar to each other. I didn't do this for you guys, but in the fluids class I did. You could do Buckingham pi, and Buckingham pi results in the fact that you get a dimensionless length. So boundary layer height divided by length down the plate, which is x, is proportional to the Reynolds number raised to some exponent. So this relationship comes from Buckingham pi. And then what we're going to do to get a similarity variable is we're going to put these two pieces of information together, right? So eta is proportional to y over x times Reynolds number to the 1/2. That's the combination of these two. And the thing that's so powerful about this is that I've just taken basically a two-dimensional problem that had variables in x and variables in y, and I've converted it into a one-dimensional problem, right? I just now have this variable eta, which in addition to containing all the information about y and x, also is my stretching factor that gets me from one velocity profile to the next, to the next, to the next in the flat plate just by stretching them. So it turns out, because of that stretching, that scaling property of eta, that the first derivative of this solution to Navier-Stokes, the Blasius solution, is equal to the local velocity. So wherever you happen to be in the boundary layer, xy, non-dimensionalized by the free stream velocity, that is the first derivative of this function. So with all of this information, we can now actually find like numerical values that get us to these numbers in these correlations. So here's what we're going to do. We're going to say, okay, right? Engineers set the boundary layer thickness delta at the spot where the local velocity is 99% of the free stream velocity, right? So that's this statement. And we know that this ratio of local velocity to free stream velocity is the first derivative of this function, which is a function of eta. So we're going to set that value to 99% or 0.99. And then we're going to find the appropriate eta value that solves this guy at the edge of the boundary layer. And that is the eta that we're going to plug into our, oh, no, it's here. That's the eta that we're going to plug into our relationship between the boundary layer growth and the Reynolds number to actually like get a numerical value, right? To come up with an equation that relates these two instead of just this correlation sign, right? This relative value sign. Okay, so we're going to do that in the next slide. Okay, so here's our u over u is a first derivative function of eta. Here is our value for eta. We're going to actually look at this plot. This is the solution to the Blasius equation, and it's on the x-axis, we have our dimensionless velocity, right, which is our first derivative of the function of eta, which is equal to u over capital U, u over big U. And we know that at the boundary layer, that value is 0.99, right? So what we're interested in is trying to find the value for eta at that spot, which tells us how tall the boundary layer is, right? So here's 0.99. We're going to read up to where it crosses the plot, and then we're going to read over, and it's about 5, right? And so you can actually see this. You can see it graphically here, but you can also see it in tabulated form. So this is the tabulated solutions to the Blasius equation. I will mention that there is no like finite solution to the Blasius equation. It's solved numerically, but you guys have seen that done already, right? For things like temperature field and a flat plate, right? You just take the number of terms that you need to get the number of digits here where these numbers don't change for engineering purposes, and that's considered the solution from an engineering perspective. And so 0.99, right, which is this derivative, is about equal to 5, right? It's a little bit more, 0.9915. So this is going to be, maybe a little bit less. But the kind of universally accepted convention is that the eta value at the edge of the boundary layer is 5.0. And so here's our eta equation, right? So we're going to plug in 5 here for our eta value. And what we're interested in now is a relationship between the boundary layer height, x, and whatever these variables are on the inside. So I'm going to rearrange everything. And what I end up with is a dimensionless length, right? So this is the boundary layer height per distance down the plate is equal to 5. That's the number that I found here, divided by square root of the Reynolds number at that particular spot, right? Because this combination of variables, right, gets me the Reynolds number. The x comes out, but then there has to be an x in the numerator for this x to come out of the denominator, and that gets me the Reynolds number. So this is my correlation for the growth of the velocity boundary layer, solved more or less, right, through a closed form analytical solution, with the only caveat being that these solutions are found numerically by just taking the appropriate number of terms to get the right number of digits to be able to plug in numbers that give me, reasonable precision for these results. Okay, so that's where this correlation and that's where this 5 comes from. I can do the same thing for the friction at the plate, just by noticing, right, there's a 2 here, and this is 0.644. So half of that is 0.332. Notice here the second derivative, 0.332, that's at eta equals 0, which is the edge of the plate. So that's where this value comes from. I will not go through the gory details of exactly where this relationship comes from. It would have been covered in your fluids class, but there's another correlation for that one, and ultimately we build up to get a drag coefficient. That's what we do in fluids. In heat transfer, we're interested in the thermal boundary layer, right? Because we're trying to solve a heat transfer problem. So can we apply everything that we just went through, right? And a miracle happens to come up with the size of the thermal boundary layer, and then use the size of the thermal boundary layer to figure out how much heat we're transferring from this plate into the free stream. Okay, so we're about to embark on that process. So what I want to point out to you is that this chart is the Blasius solution. It's the same as this one. The only difference is on this axis, I've non-dimensionalized, this is the book, is non-dimensionalized by 5, right? Why 5? Because 5 is the edge of the boundary layer, right? So here at the edge of the boundary layer, the value of this axis, the y-axis, is 1, and at the plate, it's 0. And then this is our dimensionless velocity, right? So at the plate, that velocity is 0. And then at the edge of the boundary layer, that velocity is 0.99, right? It's about 1. So that's what this guy looks like, and this is what that dimensionless velocity profile looks like. Okay, we want a thermal boundary layer, right? And so we're going to use the exact same non-dimensionalization on the y-axis, right? So it's going to go from 0 to 1. And instead of having a dimensionless velocity, we're going to have a dimensionless temperature. Now, the book does this in kind of a weird way, kind of confusing. Not sure why they do it this way, but instead of plotting just a dimensionless temperature, they plot 1 minus the dimensionless temperature. And I think the reason that they do that is because the plate is heating rather than cooling. I talked about this before. And so they want this number to start at 1, which represents high temperature at the plate, and then go up to 0, which represents the free stream temperature right at the edge of the thermal boundary layer. So I think that's why they do this. This 1 minus T star thing doesn't appear anywhere else except in this chart. But I just wanted to point that out to you, that you're basically looking at like 1 minus the actual shape of the thermal boundary layer. Okay, all it does is just flip the direction of this thing. So you're looking at basically a mirror image of it. Okay, so unlike the velocity boundary layer, the thermal boundary layer starts hot at high temperature, usually, right? Because we're heating the plate, and then it gets colder as we progress up towards the free stream. The other thing that's different, which I'll point out, is that this curve, the thermal boundary layer curve, is a function of the Prandtl number, whereas there was just one curve for the velocity profile. There are infinitely many curves for the thermal profile, and each one of those is a different function of the Prandtl number. So we'll get into this in a second. Okay, so here we are. I want to use everything that I determined before to figure out what the shape of this thermal boundary layer is. And the argument is, because I know the Blasius solution for velocity, I can figure out basically the equivalent Blasius solution for the thermal boundary layer. So first thing I want to do is non-dimensionalize my temperature. So I come up with this thing called T star. T is the temperature at any spot X and Y inside the boundary layer. And I'm just non-dimensionalizing that by subtracting the surface temperature of the plate and then non-dimensionalizing by T infinity minus the surface temperature of the plate. So if you look at this, right, we'll jump down here for a second. If I wanted to set the boundary conditions at 0, right, so at like Y equals 0, that's the surface of the plate. T is T surface, so T surface minus T surface is 0, and T star is 0. So T at the surface of the plate is, or T star at the surface of the plate is 0. Up at the free stream, right, at the edge of the boundary layer and beyond, T is just the free stream temperature, T infinity. So T infinity minus Ts over T infinity minus Ts is 1, and that's also the boundary condition here, right? So at Y equals infinity, T star is equal to 1. So when we get to boundary conditions, you'll know what those are and where they came from. Okay, so we got to this equation by basically canceling out all the terms that we didn't need from the Navier-Stokes equations. It turns out by kind of a miracle that if you look at the energy equation inside the boundary layer, you get the exact same form, right? So here is consider the so this is the energy equation. This is the energy equation, right? So I want to compare this one to this one, and notice I've got u du dx, v du dy, right? Second derivative u y squared. Same thing is true here, right? I've got a velocity, and then I've got dt dx. I've got a velocity in the y direction, dt dy. Then I've got some constant times the second derivative of t with respect to one of these two variables. Happens in this case to be in the y direction, right? So it's basically the exact same equation. So what this is telling me is that I can use everything that I figured out from the Blasius solution to figure out the size and the makeup of the thermal boundary layer, right? So incredibly, incredibly cool and powerful, and lucky that it worked out this way. So we're going to take this equation, energy equation in the boundary layer. We're going to substitute T star in for T. So here I am substituting T star in for T. And notice this equation is the same as the Blasius solution, with one sort of interesting caveat, which is in the Blasius solution, I've got just like a 1/2 sitting here in the middle term, and in the heat transfer solution, I have 1/2. Whoops! Oh, here it is. No, here it is. I have 1/2 times the Prandtl number, right? So remember how I was talking about how there's all these different solutions and they're all functions of Prandtl number? That's why, because in the velocity equation, there's just a constant here, 1/2. In the heat transfer equation, it's half of the Prandtl number. So as the Prandtl number changes, this shape changes in a corresponding way. But the Prandtl number is just a constant, right? It's a constant depending on what fluid it is that you're dealing with. And so I could use the exact same solution that I came up with for the Blasius equation for the heat transfer equation in the boundary layer, right? It's incredibly powerful and incredibly fortunate that it worked out this way. So the way that I do this is to note that here's the Blasius equation. So it's f third derivative of f plus 1/2 f times second derivative of f is equal to 0. Realizing that u over capital U is equal to u star, this dimensionless velocity we've been talking about, and that is the first derivative of this function. I can then go in and basically just rewrite this guy as this guy, right? So d squared u star over d eta squared plus 1/2 function of eta times du star over d eta equals 0, right? These are the same equation. One point of confusion, and I actually had to look this up because I'm like, well, look, if u star is f prime, right? Why is this f not like the integral of f, right? Why don't you bump this up by like an integration here? And I had to look this up because that seemed reasonable to me. So it turns out the reason we don't do it is because we already know the solution to the Blasius equation, right? You already know that, and so there's actually no mathematical benefit to bumping this up if you just leave it as this known function of eta, right? So it appears here in red and it appears here in red, just to remind you that the reason this doesn't get bumped up is because we already know the solution, right? And so the same is true here, right? The reason that this doesn't somehow change is because this is that same function of eta from the velocity, from the Blasius solution. Okay, so how cool is this, right? We basically now got a way to solve the temperature field inside the thermal boundary layer from the velocity field inside the momentum boundary layer, right? This couldn't be like more amazing and ideal. Okay, one little aside that I want to mention is in the special situation where the Prandtl number is equal to 1, which is actually almost true for most gases, right? For air, it's 0.7. For other gases, it's 0.8, 0.9, 1.1. This equation basically becomes identically this equation. And so if you're ever in a situation where you need to do just a quick back of the envelope calculation and you know what's going on in a boundary layer velocity field, you can always just say, look, if the working fluid is air or some gas, I'm just going to guess that the Prandtl number is pretty darn close to 1, and I'm just going to take the velocity field solution and I'm going to apply that to the thermal boundary layer. That is oftentimes good enough for a back of the envelope calculation. That, by the way, was actually the final exam question in my undergraduate heat transfer class when I took the class 1,000 years ago. And so I have never forgotten because I got it wrong when I took the class. So I've never forgotten that relationship. So for Prandtl number equals 1, this equation for heat transfer and this equation for the momentum conservation Blasius solution velocity profile, they're identical, right? So you can use the exact same answers. What ends up happening when you have a Prandtl number that's not equal to 1 is the boundary layer will get shorter if the Prandtl number is bigger than 1. So we see that here, right? So here's 0.6, which is the Prandtl number for air at room temperature, more or less, right? And so the boundary layer is actually getting taller as the Prandtl number gets bigger. And then for a situation where the Prandtl number is less than 1. So things like, water. So here we have a Prandtl number. Oh, no, sorry. Oh, I've got these backwards. Okay, so what I said was backwards. Thermal boundary layer is shorter than the momentum boundary layer for Prandtl number greater than 1. Oh, sorry. Blah. Okay. I'm comparing these to each other. I'm like, what? I'm backwards. No. Sorry. So what I'm doing here is I'm comparing the wrong thing. I'm comparing the thermal boundary layer to the momentum boundary layer, right? So sorry, scratch what I just said about these things changing. They do change. They change for a different reason. That's the next slide. Sorry. So let me repeat this and say it correctly. So the thermal boundary layer is going to be shorter than the momentum boundary layer for Prandtl number greater than 1. There we go. And the boundary layer is going to be taller than the momentum boundary layer for Prandtl number less than 1. Okay, that's the correct thing. All right. Now let's go back to what I was saying before, and let me make sure that I say it correctly. Um, it turns out for Prandtl numbers greater than 0.6, so basically all air, like liquids, most gases, this is true. It's only not true for a couple of strange cases. It turns out that this derivative of temperature with respect to eta at the surface of the plate, all of these curves all collapse into this single equation, which is 0.332 times Prandtl number raised to the 1/3 power. This is determined in multiple different ways, right? You can see, where is it? Here, right? There's a 0.332. So tau at the wall, right, has that number in it. So that can be used to prove that this is correct. It can also just be proven empirically, experimentally. That's what the book chooses to do. What I've done is basically zoomed in on this corner and pointed out that all of these curves basically at um, uh, the plate, which is 1 minus t star is equal to 0, basically all converge to the same spot. So they're all at the same spot. And if you plug in the Prandtl numbers for each of these spots, you get like different slopes. But all of these slopes all correspond to this this correlation. So 0.332 times Prandtl number of the 1/3 power. So that's one important piece of information that's going to get us to the correlation that we need. So stand by, just hold that in mind. And I should mention, by the way, this is an AI generated figure. I just gave this plot to AI, actually this plot to AI, and I said, just zoom in on this little lower right-hand corner, and that's what it did. There is no guarantee that these lines are correct, right? This is for entertainment purposes only because this is AI generated. Okay, so we have that this derivative at the wall is equal to this value. From an energy balance at the wall, right? So here is my conduction up through the wall, and then here's my convection away from the wall. I can get the other piece of information that I need to come up with the needed correlation. First thing I have to do is figure out what T is in terms of T star, because I want everything to be non-dimensionalized. So I'm going to solve for T in terms of T star. So here's my solution there. And then if I take the derivative with respect to y, it just becomes T infinity minus T at the surface, multiplied by the derivative of T star with respect to y. Okay, I can then take this value for dt star dy and plug it into my original expression, which is what I'm doing right here, right? So I'm going to take h and I'm going to isolate it all by itself. I'm going to take this derivative and I'm going to substitute this guy in for it. And I'm going to get this ratio of T infinity minus TS divided by TS minus T infinity. This K and this K are the same, right? So I'm just rewriting my energy balance in terms of my non-dimensionalized temperature. And then I'm going to, so I'm going to now go from Y, which is my dimensional height, to eta, which is my similarity variable height, right? So how do I do that? Well, remember, where's eta? Where is it? There it is. Here's my eta equation, right? So I'm going to take my eta equation and I'm going to solve Y for eta, and then I'm going to plug in here. And what pops out is all this stuff that kind of looks like the Reynolds number, right? Except it's got X in the denominator instead of in the numerator. But we will see in a second how that gets resolved. So now I've got this expression for H sub X, but I've got this pesky derivative, right? dt star d eta at the wall. How do I resolve that? Well, remember, we just did it empirically, right? That's what this was. So I'm going to take this 0.332 times Prandtl number to the 1/3, which is equal to that derivative. I'm going to plug it in here, and boom, out pops my correlation. Now, I solved this guy in terms of H sub x, right? That is the convective heat transfer coefficient for laminar flow. That is something that I need, but I want this thing to be non-dimensionalized so that I can use it in myriad other situations, right? I've only solved this for one situation here. I want to non-dimensionalize it. So I'm going to move everything around and I'm going to define this thing called the Nusselt number, which is hx, h sub x times x over k, right? So this k is this k, this x is this x. That's where the Reynolds number comes from, right? Because moving this x out forces an x to appear in the numerator. And so I've now got my Nusselt number, h sub x times x over k. It's non-dimensional, right? So I can use it for similarity solutions. And it equals this correlation, 0.332 times Reynolds number based on x to the 1/2 times Prandtl number to the 1/3. Whoa, right? Like incredible, right? This is my heat transfer correlation for laminar flow over a flat plate, right? We just literally derived it almost from scratch using the Blasius solution, right? It's awesome, incredibly powerful. There is a caveat, right, which is this the slope of this temperature is only true for Prandtl number greater than 0.6. So this correlation is only true for Prandtl numbers that are greater than or equal to about 0.6. I will show you later on, there's a correlation for Prandtl numbers that aren't in this range, but this is a very easy correlation to use, right? You've already, by this point in solving a problem, calculated the Reynolds number. So you just plug in the Reynolds number, you look up the Prandtl number for your gas, you get the dimensionless heat transfer coefficient, and then you know the K value for the fluid. And so you can come up with H at your particular X value, right? So really easy to use, which is why this one is the one that the book goes through in detail. Okay. As a quick caveat, quick sort of addition here, we're probably also interested in the height of the thermal boundary layer, right? So this is the region where the temperature of the plate has some influence over the heat transfer process. For Prandtl numbers greater than 0.6, right? So basically from this conclusion, we also end up concluding that the ratio of the velocity boundary layer and the thermal boundary layer are about equal to Prandtl number to the 1/3 power. So this is where these different lines come in, right? That I was talking about before. The book has 0.523 kind of boxed here. And I'm like, why did they do that? They did that because this lower dotted line has a Prandtl number of 7, which is water at room temperature. And so this value turns out to be, kind of important or meaningful because it represents the height of the thermal boundary layer for water, right, in this dimensionless construction here. If I've got my ratio of the velocity to the thermal boundary layer equal to Prandtl number to the 1/7 or to the 1/3 power, I plug in my Prandtl number for the fluid. In this case, 7 for water, I get 1.19, and that gives me Oh, okay. I'm like, why? I flipped this over, right? Okay. Ha. So this gives me the relationship between the thermal boundary layer and delta, which is 0.5 532. And remember what I was saying before when I got mixed up, right? These things are actually related, right? So for boundary layer shorter than the so for Prandtl number greater than 1, the thermal boundary layer is shorter than the momentum boundary layer, right? Which is true in this case, Prandtl number of 7 greater than 1. And by, lo and behold, the thermal boundary layer is less than the velocity boundary layer, right? Because this is a number less than 1, right? So these two things are related. I got a little confused there, but they are actually related to each other because this end result just verifies the statement that I was making here. So that's why I was like trying to explain these in the context of this. So I got mixed up. Okay, cool. So we have our first heat transfer correlation. Now, let me just mention, right? I probably should have said this before, but if you took fluids with me, right, you know that my overall philosophy in that class is that we are engineers and it really doesn't matter how any of this stuff gets derived, right? It's just so long as you know the correlations, you know how to apply them. That's really all I cared about in fluids. So I was very, very light on the derivations. Heat transfer is a very different animal. A lot of heat transfer problems end up getting solved by taking the correlations and going back one or two steps into the derivation and making a change, making a modification, having like an epiphany, a realization, and then changing the correlation and moving the value, forward to a solution. So in heat transfer, it's actually important that you know where all these things come from, because a lot of these problems end up getting solved by like manipulating the correlations to get you to a correlation that's representative of your particular situation. So if you're used to, kind of the hand wavy no derivation version of energy thermal fluids that I taught you in the fluids class, this probably seems very heavy handed, but there's a reason for it. It's because we need to know where all these correlations come from to be able to modify them, to be able to come up with solutions to the problems that we're faced with in heat transfer. Okay, so we have our first correlation. We are now going to apply our recognition that if you've solved a heat transfer problem, you've also solved the equivalent mass transfer problem to get an additional, basically free correlation from the work that we've already done. So here is the species concentration equation in the boundary layer, right? So when I say species concentration, I'm talking about the relative density, the species concentration density of species A in species B, right? So these are different chemical species. So like water vapor and air, for example, A is water vapor and B is air. I've said that a couple times, but wanted to reiterate. It turns out that the species concentration conservation equation in the boundary layer has exactly the same form as, oh, I don't even need to do that. It's right here. Has the same form as the boundary layer energy equation, right? These are one-to-one analogous to each other. The only thing that I've changed is instead of temperature, I've got the density of species A. And instead of the thermal diffusivity, I've just got the diffusion coefficient, right? But the form of the equation itself is exactly the same. Derivative with respect to x plus derivative with respect to y equals second derivative with respect to y squared, right? So exactly the same. What that means is that we can use all of the stuff that we just did to derive this guy to create a parallel, analogous mass transfer correlation, right? Which then allows us to solve for things like the evaporation rate out of pools of water and so forth. So this is not a mass transfer class, but you basically get all these correlations for free, right? So we might as well talk about them so that you can use them in situations where you're dealing with evaporation and mass transfer. So to get from here to here, we just have to replace alpha with DAB, and we have to replace T with a dimensionless species density, which we can do in the exact same way that we did for temperature. So this is the species density at any value or at any location inside the boundary layer, X, Y. This is the species concentration at the surface of, so imagine you're trying to find like the evaporation rate from a pool of water. This is like, right at the surface of the water. So 100% relative humidity right above the water. And then that gets non-dimensionalized by the species density up in the free stream minus the same free stream, the same species density at the surface. This, by the way, you can find from a psychrometric chart knowing the relative humidity, right? It's basically how much water vapor is dissolved in the air that's blowing over whatever lake or stream or whatever body of water you're trying to figure out the evaporation rate for. In a lot of the problems that we solve, we're just going to assume that this is zero, right? So no humidity in the air. But you could find this, right, using relative humidity from thermodynamics. Okay, so we're going to take this dimensionless species density. We're going to plug it into our original species density equation, conservation equation, and out pops this expression. This expression is identical to the expression that we had before for the thermal boundary layer, with the exception that in the thermal boundary layer, we had the Prandtl number. In the mass concentration boundary layer, we have the Schmidt number. Remember, Schmidt number is the viscosity divided by the diffusion coefficient. But these two are identical, right? They're identical in every way mathematically. So what that means is that we can go through exactly the same thing we did before, right? So we're going to set the boundary conditions the same way. So uh, if rho A star is 0, what that means is that rho A is equal to rho AS. So that is the value of the species density at the surface of the fluid, right? So this value minus this value is 0 at that spot. So hence that boundary condition. And then far away from the free stream, this value just becomes rho A infinity, right? So you have rho A infinity minus rho AS divided by rho A infinity minus rho AS. That's 1. So that's where this boundary condition comes from. Notice, right? They're the same boundary conditions that we had before. This is identical in every way. And so voila, without doing any more math, without doing any more like weird hand wavy, scary stuff, out pops a correlation for the Sherwood number, right? Which again is a dimensionless mass transfer coefficient for some specific location X in the laminar flow portion of a flat plate, right? And it's the exact same values, right? The coefficient is the same. The exponents are the same. The only thing that changes, instead of Prandtl number, we have Schmidt number. There's even an analogy for the growth of the concentration boundary layer, right? So for Schmidt number greater than 0.6, which is basically most gases, everything else, that ratio is also just Schmidt number to the 1/3, right? The same way as this was Prandtl number to the 1/3 for the relationship between the velocity and the thermal boundary layer. So if you know the size at a particular spot of the velocity boundary layer, you now know the size of the thermal boundary layer and the mass concentration boundary layer from this relationship for Schmidt number greater than 0.6, right? How cool is this, right? This is like super useful and super powerful. You guys are like, undergrad mechanical engineers, and now we can do evaporation problems, right? It's awesome. I love heat transfer. Okay. All right. So let's talk about some key conclusions and then just wait. This is laminar flow, right? There's all of turbulent flow still in front of us. Okay. So some key laminar boundary layer conclusions for local heat and mass transfer. Shear at the wall, the mass transfer and heat transfer convection coefficients all decrease as x equals minus 1/2 from the leading edge for 0 to x to x sub c, the critical location, critical Reynolds number, where we transition to turbulent flow, right? So this is sort of the trend at which all of these change. So in other words, the shear, heat transfer, and mass transfer are all really high at, let's see if we can find a plate here. Here. Really, really, really high at the leading edge of the plate, and they actually get lower as you cruise down the plate, right? So high at the start of the plate and get low as you cruise down the plate. And they lower as x to the 1/2. Also, for most gases, Prandtl number is about equal to 1. The Schmidt number is about equal to 1. And so these boundary layers grow at, more or less the same rate, right? Slightly different, but, for engineering purposes, you can usually make this assumption, get away with it, that all these boundary layers are all on top of each other. Okay. So we've talked about local convection coefficients. We now need an average convection coefficient for the entire length of the plate. So the way that we're going to do that is take our local correlation, which is a function of x, and we're going to integrate it all the way down the plate to some, location x that we're interested in. And the end result is going to now be a correlation that's good for an entire distance down a plate from the leading edge of the plate to some location x. So that's what I do here. So I say h bar sub x, right? You should recognize this as the average convection coefficient, is equal to 1 over x, right? So I'm taking the average of the integral from 0 to x of h sub x dx. I know H sub x, right? Because that's my correlation, right? So here I am plugging it in, right? There's the correlation. And what's left is dx um, and x to the 1/2. One sort of subtlety here that I do want to point out is um, I'm going to check on this. I'm going to check on this. This x might end up being inside here, right? Because this is Reynolds number to the 1/2. Yeah. Okay. I'm gonna check on this. So let me make a note to check on this slide. Um, yeah, this X might end up in here. So I'll check on that. The end result though is correct. I've checked it with the book. So what ends up coming out of this is that you end up with the average heat transfer coefficient for a distance on the plate, some length X, is just equal to 2 times the local heat transfer coefficient at that spot, right? And so knowing that, we can just take our original Nusselt number. Where is it? Our original Nusselt number correlation and just multiply by 2, right? Because I'm just multiplying this by 2, which means I'm multiplying this by 2, which means that the average Nusselt number for some distance down the plate, x, is just equal to 0.664 times Reynolds number at that spot to the 1/2 times Prandtl number to the 1/3. And this, of course, is true for Prandtl number greater than 0.06 because this whole thing is based on this empirical observation, right, which is only true for Prandtl number greater than 0.06, 0.6. And in parallel, we can do the same thing for the Sherwood number because everything for the Nusselt number is identical to the Sherwood number with the exception of K gets swapped out for D, the diffusion coefficient. So we get 0.66 times the Reynolds number to the 1/2 power times the Schmidt number to the 1/3 power. And that also is only true for Schmidt number greater than 0.6. But that's true for like most gases, right? And most fluids. This is true. Okay. So these are our average Nusselt number correlations for some distance down the plate, provided the flow stays laminar down the plate. And just as kind of a sanity check, right, we want to go back and remember that originally, way back here, way back here, right, we posited this as the equation for these average Nusselt number values, right? C times Reynolds number to the M times Prandtl number to the N. And lo and behold, we make our way back. Yes, right? These are those same forms that I just showed you on that slide that we started out with. And look, Nusselt number, average value for some distance down the plate is equal to some constant times Reynolds number to the 1/2 times Prandtl number to the 1/3. It's exactly the same form that I promised it would be, right? So this is a really good sanity check. This is like, you know you're in a good place when you basically get the same answer by attacking the problem from multiple different ways, right? These relationships came from Buckingham Pi, and these came from the Blasius solution, right? And they agree with each other. So awesome. Okay. I will mention that for flow over the entire plate, right? So this is some X value, right? It doesn't have to be the whole plate. It could be any coordinate down the plate to whatever distance you want, so long as you're still in laminar flow. But if you want the entire plate, provided you have not transitioned to turbulence, provided you haven't crossed that critical Reynolds number, you just put an L here, right? So length of the plate, and then this becomes a correlation for the average Nusselt number over the entire length of the plate. Okay, cool. Let's talk about the situation where the Prandtl number is not the Prandtl number is not greater than 0.6. So when you have a situation where Prandtl number is less than 0.6, which mostly is the world of liquid metals, all the previous results go out the window because this conclusion is not true for those very, very small Prandtl numbers. Why do we care so much about liquid metal? Well, it turns out liquid metal shows up all the time in heat transfer problems because metal has a very high thermal conductivity, right? So it's often used in, like, for example, nuclear power plants, like liquid sodium, as a cooling medium, right? So you do have to know how to deal with liquid metals, and you cannot use the correlations that are good for like gas and water and stuff where the Prandtl number is high. For the case where we have a very, very, very small Prandtl number, the thermal boundary layer develops much faster than the momentum boundary layer. And so you typically just assume that U is equal to big U throughout the thermal boundary layer. Um, let's see, boundary layer, thermal boundary layer develops much faster. Yeah, yeah, yeah. Okay, good. Yeah, that's self-consistent throughout the. Okay, so without doing any more derivations or kind of walking through all the steps, recognizing this difference in thermal boundary layers, you could work out that the Nusselt number is just equal to this correlation. So 0.564 times the Peclet number at some distance x down the plate raised to the 1/2 power. And this is good for Prandtl numbers less than 0.05 and for Peclet numbers greater than about 100. What's a Peclet number? A Peclet number is just another dimensionless number, which is just the Reynolds number times the Prandtl number, right? So this is very similar in form to this one, right? Except the exponent is the same in both cases. And so we just like stick them together, right? And come up with, we call it the Peclet number, right? Name it after some other person. Okay. So this is the correlation that you deal with for liquid metals if you're in a situation where your Prandtl number is much, much less than 0.6. Doesn't happen very often, but happens enough that it's in the book and it's worth mentioning. Okay. Flat plate in parallel flow. Oh, okay. So this correlation is most often used because it's simple, and it's based on the solution to the Blasius solution, right? So it's actually based on first principles and a derivation rather than experiment. It turns out that there's tons of correlations that stretch over the entire range of Prandtl numbers for Nusselt number, and this is the one that the book gives. So if you're ever in doubt about what the Prandtl number of your fluid is, you could just default to this one, right? It's a little bit more complicated. You have to figure out what the Prandtl number is and plug it in. And if the Prandtl number is less than 0.6, this is what you end up using. And this correlation is good for Peclet numbers greater than 100, right? So you gotta check the Peclet number before you can use this correlation, but it's usually good for most fluids that we deal with. In parallel, right? See, this is a local value, right? I don't have a bar over it, just local value. If I want the average Nusselt number for some distance down the plate, I just multiply this by 2, right? Same thing that came out here, right? Just multiply the local value by 2 to get the average value over the plate. Okay. That was laminar flow. Now we are going to transition into turbulent flow. And just as a quick reminder, here is flow over flat plate. Here is all the laminar stuff that we talked about before. Because the fluid is laminar, the flow is well ordered. The velocity profile is well understood, well known. There's no chaotic mixing. As soon as you transition into turbulent flow, which happens at a transition Reynolds number of about 5 times 10 to the 5th, you end up with chaotic mixing, right? So the well-organized structure of the flow breaks down, and you end up with turbulence, right? Turbulence is actually good from a heat transfer perspective in that it increases and enhances the rate of heat transfer from a surface. So it's often the case that you want turbulent flow because you get more heat transfer from a surface for turbulent flow than you do from laminar flow. Just as a quick reminder, there is this kind of transition regime, and your flow gets fully turbulent when you reach a Reynolds number of about 3 times 10 to the 6. But all the solutions that we're going to talk about now are good for Reynolds numbers above 5 times 10 to the 5th. Okay. There is no closed form analytical solution analogous to the Blasius equations for turbulent flow. Everything that has to do with turbulent flow is all done empirically, all by experiment. So same geometry as before, except now I've got my turbulent boundary layer portion boxed, and that's where we're going to focus. So if you remember from your fluids class, the friction coefficient, again, empirical, is 0.0592, Reynolds number raised to the minus 1/5 power. And that's true for turbulent flow over a flat plate from this spot of transition all the way up to a Reynolds number of about 10 to the eighth. By the same token, the turbulent boundary layer thickness is, again, empirical 0.37 x times Reynolds number raised to the minus 1/5 power. And so I say here, comparing the laminar boundary layer to the turbulent boundary layer, growth is far more rapid for the turbulent boundary layer, right? So the turbulent boundary layer will actually grow as x to the 5/4, whereas the laminar boundary layer will grow as x to the 1/2. And that's exactly what you see here in this chart, right? And this one as well, right? The boundary layer grows much faster in turbulent flow than it does in laminar flow. And you should remember that from your fluids prerequisite class. The turbulent boundary layer is influenced most by random flow fluctuations, not by molecular diffusion, right? There's a lot of mixing, right? A lot of turbulence, right? The fluid is constantly getting mixed up. The momentum is getting mixed up. The thermal energy is getting mixed up in the turbulent boundary layer as a result of all those turbulent eddies. And so turbulent boundary layer growth is not dependent on Prandtl number or the Schmidt number the same way that it is in laminar boundary layers. So for turbulent boundary layer, because of all the mixing, the velocity boundary layer height growth, the turbulent thermal boundary layer height growth, and the concentration boundary layer height growth in turbulent flow are all basically identical, right? Because everything gets mixed up. Again, empirically, we can come up with a local Nusselt number correlation, which is this guy, right? So still equal to h at some location x times that location x divided by k equal to 0.0296. Reynolds number raised to the 5/4 times Prandtl number to the 1/3. Schmidt number, not Schmidt number, Sherwood number, right, is exactly the same, right? All the same numbers, same exponents for the same reasons we talked about before. Once you solve the heat transfer problem, you've also simultaneously solved the mass transfer problem, even though we're now in turbulent flow, right? All the underlying equations are still the same. The only thing that swaps out is instead of Prandtl number to the 1/3, we've got Schmidt number to the 1/3. And both of these are empirical, and the experiments were done. So these are valid for Prandtl number from about 0.6 to 60, or if you're in the mass transfer world, from a Schmidt number about 0.6 to 60. All right. Now, we've got laminar flow transitioning to turbulent flow across our plate. And if we have a plate that's long enough that we reach that critical Reynolds number, we still need to find the heat transfer from the overall plate. And so we need an average heat transfer coefficient for the whole plate. What that means is we basically have to solve for the laminar portion, and then we have to solve for the turbulent portion, then we have to stick them together, right? So I've got this whole thing boxed here. Just to remind me that now we're talking about both laminar flow and turbulent flow at the same time. So I say here, since the laminar boundary layer generally precedes the turbulent boundary layer, right? So laminar boundary layer comes first and the flow trips to turbulent. Mixed boundary layers must be considered for true convection coefficients. And by mixed, I mean laminar plus turbulent. So how do we do that? Well, we're going to do the same thing we did before, right? We're going to come up with an average convective heat transfer coefficient, and we're going to do it through an integration, but we're going to integrate, right, basically by taking an average over the full length of the plate from the leading edge of the plate up to that transition spot to get the contribution for the laminar velocity profile. And then we're going to add to that from the transition spot to the end of the plate, the contribution from the turbulent velocity profile. Add that all together, take it 1 over L to get an average, and that's going to be our average forced convection heat transfer coefficient over the entire plate, right? So here I am doing it, plugging in all the values, right? These are the correlations that we know. A bunch of this stuff is constant and comes out, right? K is constant, L is constant, the coefficients are constant, the free stream velocity is constant, the viscosity is constant. All that comes out, and what we're left with is just in the laminar part, dx over x to the 1/2, and in the turbulent part, dx over x to the 1/5. The whole thing gets multiplied by the Prandtl number to the 1/3 in the end. And the end result is this guy for the Nusselt number. And of course, once we've solved the heat transfer problem, we solved the mass transfer problem. So the value is exactly the same for the Sherwood number, just with Prandtl number swapped out for Schmidt number. Okay, because this underlying correlation or these underlying correlations were developed for the Reynolds number range, transition Reynolds number up to 10 to the 8th, and for Prandtl number in this range and Schmidt number in this range, those same requirements propagate forward to limit the range that we can use these correlations for. No problem. This is a big range of Prandtl numbers and a big range of Reynolds numbers. Notice, right, you start out with a Reynolds number at the critical Reynolds number, 5 times 10 to the 5th. No reason to use this if you haven't actually reached a plate that's long enough for the flow to transition and trip into turbulent flow, right? You would just use the laminar correlation in that case, right? So this is what gives us the lower bound here. It's not that, this is somehow like physically invalid. It's just the flow hasn't transitioned to turbulent flow until you reach this spot. The other thing that I'll just quickly mention is that the way that the book does it is it gives this leading kind of coefficient, and then it says minus A, and then A is all this extra stuff. And it turns out that is important because for the case of a completely turbulent boundary layer, A is 0. So what do I mean by a completely turbulent boundary layer? Didn't I just get through saying that laminar boundary layers precede turbulent boundary layers? Well, yeah, normally they do, but because the heat transfer is better for turbulent flow than it is for laminar flow, it is often the case that engineers will intentionally trip the flow to turbulence at the leading edge using like a turbulence wire or some other turbulence promoter, right? Something that trips up the flow and gets it kind of rotating. And by the time it gets down here, it's got some turbulence in it then. And by the time it gets down here, it just transitions anyway to turbulent flow. And so flow is turbulent all the way down the plate. So in a situation where you have intentionally tripped the flow to turbulence, you don't need to worry about everything in this A term, right? All that just goes away. And it's basically like taking the integral of this guy from 0 to x, right? Which is what this leading term essentially means. So I say that here. Condition created by tripping the boundary layer at the plate's leading edge using a wire or turbulence. For x equals, okay, so this is the critical Reynolds number. So if you're solving this exactly for the value with the critical Reynolds number, A is just this value 871. That turns out to be useful because sometimes you need to know like the value to plug in for A for a typical problem instead of having to plug in for the Reynolds number and solve it, right? You just know that at that spot it's 871. Okay, so just good piece of information to have. Okay, so that's it. That's our final correlation that includes both the laminar regime and the turbulent regime, and we have a solution for the entire turbulent regime if we want it. And we have a value for what happens if we're just interested in fluid that's just tripped to turbulence. Okay, let's add some complexity. Not that this is already not complex enough, but here we are. So a very common situation in a lot of heat transfer experiments is the so-called unheated starting length. So this is a situation where you have flow over flat plate and there's some starting length where no heat is added to the plate. And so the plate's surface temperature is the temperature of the free stream. And then as the velocity boundary layer develops at some location down the plate, which is, I think this is zeta, some zeta down the plate where um, all of a sudden you start heating the plate from that spot on. And now you have the development of a thermal boundary layer, right? So this happens a lot. In fact, in my own PhD research, when I did my PhD at MIT, I had this exact situation. So I was blowing dry, this was nitrogen, it was basically air, blowing air over a fabric. What was under the fabric was a little dish of water, and I was interested in the rate of diffusion of the water through the fabric. So this was the calibration experiment. I later did experiments where I was looking at like micro and nano engineered pores, or looking at diffusion coefficients through pores of microns down to nanometers in characteristic diameter. So if you're interested, my PhD dissertation is at the MIT library. You can look it up and read it. The point is, there was a starting distance, right? So there was this distance here where there was no heat transfer, no mass transfer. The air was blowing over this kind of plastic, overlay, this plastic cover, and then would reach my evaporation disk after some distance zeta. And so I actually used this solution in my PhD dissertation to figure out the rate of mass transfer through this calibration fabric, and eventually micro and nano engineered porous barriers. So I love this because I used this in my PhD dissertation, and I was quite surprised that it showed up in our textbook. So I wanted to just mention it. Um, Okay, so we have this unheated starting length, right? Unheated starting length, and then all of a sudden we have a portion that's heated, and so how do we handle that? The velocity boundary layer is going to start growing right from the leading edge of the plate. The thermal boundary layer is not going to start until the flow actually reaches the spot where the plate starts to get heated. And there is no heat transfer from the plate to the free stream all the way up until the free stream reaches the spot, or the boundary layer reaches the spot where the plate gets heated. So the way that we handle this is take our original convection, convection coefficients, our original Nusselt numbers, and we divide them by this correcting factor. So this factor is the quantity 1 minus zeta over x, right? Zeta, again, is that initial distance that's not heated. X is the distance down the plate that you're interested in actually finding the heat transfer. So that quantity raised to the 3/4 power, and then the whole thing raised to the 1/3 power. That ends up in the denominator for laminar flow, with that same laminar flow correlation in the numerator. And then for turbulent flow, we use our turbulent flow correlation with a similar denominator. This denominator is just, instead of using 3/4 and 1/3, it's just 9/10 and 1/9, right? So, and then I say here, analogous mass transfer results are obtained replacing the Nusselt number and the Prandtl number with the Sherwood number and the Schmidt number, right? So I don't show that here, but you could also get Sherwood number correlations for mass transfer for laminar flow and turbulent flow just by replacing Nusselt with Schmidt. Sorry, Nusselt with Sherwood, and then Prandtl number with Schmidt, which is what I actually did, right? Because I was worried about mass transfer, water vapor diffusion, mass transfer. So I used the mass transfer version of those equations. Okay. Those are the local Nusselt numbers, the local heat transfer coefficients. We also need an average heat transfer coefficient for the entire plate. So we get to the average heat transfer coefficient for the entire plate, basically by doing the same thing we did before, which is integrating, and we come out with this expression for the average Nusselt number. L is the length of the plate. Zeta is the unheated starting distance. And we have the same thing for turbulent flow, right? We just do an integration and we come up with a similar correlation. So just to note, just to be clear, the Nusselt numbers, the average Nusselt numbers for the entire length of the plate that we're getting here, give us a heat transfer coefficient H that is averaged over just the heated portion of the plate, not the full length, right? So the full length of the plate minus zeta is the part that we're talking about. So if you wanted to find the heat transfer, you'd use Newton's law of cooling to get these H values, multiply them by A, multiply them by the temperature difference to get the heat transfer. that A is the length of the plate times the width of the plate minus this starting distance, right? So don't include the starting distance. That'll give you an area that's too big. Um, Corresponding average heat transfer coefficient for the full plate must be multiplied by the heated section area um, using Newton's law of cooling to determine the plate's total heat rate, right? So that's just in writing what I just said in words, right? We're just going to use the heated area of the plate instead of the total area of the plate. Okay. We've talked about constant temperature, holding the plate at constant temperature. What happens if you have a situation where you're holding the plate at constant heat flux, which is another possibility that you might encounter. So I won't go through all the derivations. The book doesn't either, but know that there is a correlation for flow over a flat plate. This is laminar flow over a flat plate um, for constant heat flux, which is this. There's also a correlation for turbulent flow over a flat plate, again, assuming that the turbulence gets tripped from the leading edge of the plate. So this does not include, right, the leading laminar portion. This just says, whoop, I tripped the flow to turbulence here at the front of the plate, and I've got turbulent flow all the way through. That's this correlation. Here are the ranges for those. Uh, yep, because these are based on the same ranges that we got for the constant temperature plate. Um, the kind of takeaway message here is that the Nusselt number, local Nusselt number, is 30% bigger for laminar flow and only 4% bigger for turbulent flow than for the constant temperature situation, the constant temperature correlations, uh, respectively. If you wanted a laminar flow or a turbulent flow correlation for constant heat flux, where you have an unheated starting length, you can do the same thing that we did before, right here, and just multiply these correlations by this for laminar flow or this for turbulent flow. And that gives you the unheated starting length. Okay, so if you've already got the heat flux, right, which presumably you know because you have constant heat flux that you've dialed in and are setting and are maintaining in your experiment, um, you can determine the local surface temperature using Newton's law of cooling, right? So this is just Newton's law of cooling, basically just rewritten with known heat flux divided by local heat transfer coefficient in terms of a temperature at some location down the plate and the free stream temperature. Um, if heat flux is known, okay. Sorry, I just said this. This is the same equation, right? Same equation. I'm just for continuity bringing it to the next slide. Okay, the total heat rate Q. You could just determine that from the heat flux, right? So I know that Q is equal to Q double prime at the surface times the area of the surface. So it's not necessary to find an average convection coefficient if you are interested in finding Q. However, remember back to kind of like the original goal of all these heat transfer problems, which is if I know the temperature field, I want to know the heat flux, or if I know the heat flux, I want to find the temperature field. So this is a situation where you know the heat flux and you're interested in the temperature field. You can get the local temperature this way, but how do you get the average temperature, the average Ts minus T infinity for the entire plate? Well, you can do it by basically using an integration, just like we did before. So I'm going to take 1 over L times the integral from 0 to L, so the whole length of the plate, of the temperature difference across the plate times dx. I'm then going to take this expression, which, let's see. Yeah, this is from Newton's law of cooling. So I'm gonna plug it in here, right? A bunch of things come out because they're constant, right? So, well, one thing, which is Q, comes out because it's constant. The Nusselt number is a function of X, and this is interesting. K should probably come out as well because that's not a function of X. So let me check on that. 26. Okay. And then you can end up solving for this, and the solution is just Q of the surface double prime, which you know, right, times L of the plate, divided by K and the average Nusselt number for the entire length of the plate. And that's equal to the average of the temperature difference on the plate, just in case you need it. This Nusselt number, by the way, has a special form, which is this, right? So this is again from an empirical correlation. And notice, right, that this Nusselt number is only about 2% larger than the Nusselt number obtained from our expression at x equals L, right? Our Nusselt number for flat plate and laminar flow, right? So what they're doing is just comparing 0.68 to 0.66, right? It's only a 2% difference. And in turbulent flow, the differences are even smaller, right? So you don't even need to worry about it for turbulent flow. So any results obtained from uniform surface temperature may be used in this expression to evaluate T minus T infinity, right? So really what we're saying is if you know the heat flux instead of the surface temperature, there's only a 2% error in just using the constant surface temperature correlation to come up with an average surface temperature. So for engineering purposes, it's probably fine to do that, right? These guys gave us this little extra kind of 2% bonus, but not really needed. Okay. That brings us to the end of the technical content. let's solve a couple of problems to see how this works. Okay, so this, by the way, is a very, very cool example. I really, really like this. We're going to consider flow over flat plate, two cases involving parallel flow of dry air at a velocity, upstream free stream velocity of 1 meter per second and a temperature of 318.15 Kelvin, right? I have done you the service of converting Celsius to Kelvin, so you don't have to do it. And this temperature and then atmospheric pressure over isothermal plate, so a plate maintained at constant temperature of 293.15 Kelvin. In the first case, the flow transitions to turbulence at Reynolds number equal to 5 times 10 to the fifth, right? So this is the normal situation, right? Where the flow starts out as laminar and then it transitions to turbulence at the critical X value. In the second case, the flow is intentionally tripped to turbulence at x equals 0, right? So there's a little turbulence perturbation, little wire, something like that here that trips the flow to turbulence. And the question is, at what x location are the thermal boundary layer thicknesses of the two cases equal, right? So we have a thermal boundary layer growing naturally with no trip to turbulence, and then we have a thermal boundary layer that's growing as a result of an artificial trip to turbulence. And the question is, at what spot, at what x coordinate down the plate, do those two boundary layers match each other in height? And then once we have that location, what are the local heat fluxes at that location, right? So what's the Nusselt number at that spot, and then the corresponding Q value for that spot. Okay, so a couple of assumptions which are common for these types of problems. First is we're going to assume steady state conditions. Then we're going to assume this is a boundary layer, right? All the action happens in the boundary layer, so the boundary layer assumptions apply. And then third is that we're going to have constant properties, right? So we're not going to change properties inside the boundary layer. All right. As a reminder, right? I said I would bring this up again. As a reminder, this is our methodology, right? So we're going to remember that all action happens in the boundary layer, identify the geometry, specify the reference temperature. This is not a mass transfer problem, so we skip step 4. Evaluate the pertinent fluid properties at the reference temperature, calculate the Reynolds number, determine whether the flow is laminar or turbulent, decide whether the problem requires a local or average coefficient, select the appropriate Nusselt number in this case, right? It's not mass transfer, it's heat transfer, so Nusselt number, plug in the parameters and solve for the heat transfer coefficient, and then take that heat transfer coefficient, plug it into Newton's law of cooling, and get the heat flux. So that's what we're going to do. We have already silently repeated to ourselves that all action happens in the boundary layer. We've also identified the geometry as flow over a flat plate, right? It's a flat plate, so we don't need to worry about that. Step 3 is specify the reference temperature. So we know that the plate is at 318 Kelvin and the free stream is at 293 Kelvin. Yeah. Oh, no, 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 no. I got it backwards. Sorry. The air is hot, right? So this is a situation where the plate is actually colder than the air. Doesn't matter. The film temperature is the same either way. So I'm going to take 318 and 293, and I'm going to add them together, divide by two. That's the average. So 305. Um, Back in my day, 1,000 years ago, right, and probably you guys had to do this in thermo, you would get a table that has properties, and you'd have to like interpolate between two entries in that table. In 2026, we have AI to do that for us. And so I just asked AI to give me the properties of air at 305.65 Kelvin, and this is what it gave me. Now, very important to just not blindly trust AI. AI hallucinates, AI misinterprets, AI gets things wrong. Always important to just do a little sanity check to make sure that anything you get from AI makes sense. So I have a table from our book where I actually know all the properties at air for 300 Kelvin, which is pretty darn close to 305. So I'm checking. So 26.3 times 10 to the minus third, 26.7. Yep. Okay. So those numbers are the same, right? Notice that this is just this guy and this guy are just different by 10 to the third, right? So that's just, the book trying to, reduce having to type a bunch of decimal places. The viscosity, let's see, 1.62 times 10 to the minus fifth, 1.59 times 10 to the minus six. Okay, so those are pretty similar, right? So that's good. Prandtl number, 0.707, 0.705. Okay, so these seem to check out, right? They're pretty close to the values that I would actually expect. So I'm going to go ahead and use these AI generated values. If you do not trust them, you can interpolate. You can look up on a more refined table. You can actually go to like a software package like Engineering Equation Solver, and a lot of these values are tabulated, and you can look them up within the equation. So all those are also viable solutions. But whenever you use AI, make sure that you're verifying what it gives you by checking some other source. Okay, so we're going to just do this in parallel. So for laminar flow, this is our velocity boundary layer, right? We know that this is the exact solution from the Blasius equation. We also know that for Prandtl numbers greater than 0.6, that the ratio between the laminar velocity boundary layer and the laminar thermal boundary layer, this should be subscript T. Let me change that in the final slides. Subscript T is equal to about Prandtl number raised to the 1/3 power. I got to check to make sure that my Prandtl number is in fact greater than 0.6. It's 0.7, so that's legit. That checks out. And for turbulent flow, here is my boundary layer growth. And remember, because of all of that turbulent mixing, where is it? There it is, right? All that turbulent mixing, the turbulent velocity, temperature, and mass concentration boundary layers are all the same, right? So don't need to worry about multiplying anything by Prandtl number or anything like that. They're the same. Okay, so I can then say, all right, I'm going to set these two equal to each other. So turbulent thermal boundary layer equal in height to laminar thermal boundary layer. I know the equation for the laminar thermal boundary layer, which is here. I just took this, multiplied it by Prandtl number to the minus 1/3, right? Because I'm solving, right? This guy goes in the denominator there. And then I'm going to set that equal to the height of the turbulent thermal boundary layer, which happens to be the same as the turbulent momentum boundary layer, velocity boundary layer, right? So basically setting these two equal to each other through these equations that represent how big they are. The Reynolds number is in here. Reynolds number has X in it. That's how I get to my X value. So this is just borrowed from that previous slide, right? This equation is just this equation. And now I'm solving this for the Reynolds number, right? So I'm pulling all the constants out. I'm getting the Reynolds number all by itself. And what I end up with is that the Reynolds number is equal to all this stuff, right? 5 times the Prandtl number to the minus 1/3 divided by 0.037. Yep, 0.037 raised to the 10 over 3. Weird exponent, but it comes from the fact that I'm basically combining this Reynolds number exponent with this Reynolds number exponent. And what I end up with is 8,667.8. just as a quick aside, later on, right, they've asked me to find the local heat fluxes. I could have just solved this all the way through and found X, right? I'm going to do that in the next step, right? Just by multiplying and dividing by velocity and viscosity. I did not do that because I need the Reynolds number for later, right? So I just solved this as an intermediary step because I'm going to plug in the Reynolds number into the Nusselt number later on. So that's why I did it this way. Okay, step number 7 is determine whether the flow is laminar or turbulent. We expect the flow to be laminar because of the way the problem is phrased, right? So um, in the first case, we have a laminar boundary layer, and we have a crossing point. And then in the second case, we have an intentionally tripped boundary layer. And so given the way that the problem is written, we expect this value to be less than 5 times 10 to the fifth, so that we are still inside the laminar boundary layer for the laminar part of the solution process. And lo and behold, whoop, too far. Lo and behold, that's what we get, right? So laminar Reynolds number is expected, and that's what we have. So good. And then we also have to remember that the flow is tripped to turbulence for the second part of the problem. Okay, so I know the Reynolds number for both of these. So I can now solve for X. And here I am doing that. So here's the viscosity, here's the velocity. Just multiply those by the Reynolds number, and I get 0.1404 meters, right? So what is that, about 14 centimeters? Which that checks out with the solution that comes from the book and from AI. So I'm pretty confident on that one. I now have to solve the heat transfer part of the problem. So we're asked to decide whether the problem requires a local or a surfaced average coefficient. Remember that we're asked to find local heat fluxes at a particular location. And so we're going to determine the local Nusselt number, which is going to give us the local H value, which is going to give us the local heat transfer. So I've got local highlighted here in red. We're going to select the appropriate Nusselt or Sherwood number correlation, plug in the parameters, and solve for H. So here I am doing that for the laminar boundary layer, the one that was not tripped to turbulence. I'm using the laminar Nusselt number, and I'm solving for H, right? So here I am putting in all the numbers, all the numbers, all the numbers. Here's that Reynolds number that I solved for before, right? That's why I left it, so that I would just be able to plug it in. So plugging in the numbers, and out pops a laminar forced convection coefficient of 5.23 watts per meter Kelvin. I think that's watts per meter squared Kelvin. Let me check on that. I'll correct it if it's wrong. And then here I am doing the same thing for turbulent, right? So here's our turbulent boundary layer, or turbulent Nusselt number correlation. Here I am solving. Here's that Reynolds number again, same Reynolds number because it's the same spot, right? Solving, and out pops 7.04 watts per meter squared Kelvin. Pretty sure it's meter squared. Okay, cool. So I've got my numbers. At this point, I can do a sanity check, right? Always good to build a sanity check into all of your solutions so that you can just make sure that you're on the right track. You're not spending a ton of time and effort solving a problem where you've already messed up on a previous step. We expect the turbulent convective coefficient to exceed the laminar coefficient, right? Because we talked about how mixing promotes right, the transfer of thermal energy inside the turbulent boundary layer. And lo and behold, it is in fact bigger. Turbulent is bigger than laminar. And so that's exactly what we expect. So that's awesome. Checks out. Suggests that we can move on to actually solving for the heat values. Oh, and look, watts per meter squared Kelvin, right? I was right. So I'll correct that in the previous slide when I post the final version of this. So here's Newton's law of cooling, right? So I'm looking at watts per meter squared at that particular spot. I know the convective heat transfer coefficient at that spot. I know the temperature difference because that was given in the problem. So here I am just plugging in the numbers, and I get minus 130.8 watts per meter squared. Minus, why is it minus? Well, it's minus because, remember, the plate is colder than the air. And so I'm getting heat transfer into the plate, and heat transfer into the plate is negative in this case because the convection coefficient, remember, is always written with the bigger number first and the smaller number second so that the value is always positive. So this minus sign comes from the convention of bigger number first, smaller number second for convective, for Newton's law of cooling, right? So that's where this negative sign comes from. I do the same thing for turbulent flow. Here's my convection coefficient from the previous part. Here's my temperature difference. I get minus 107, 177, right? Minus 177 watts per meter squared. Heat transfer at that spot, right? And again, we expect this number to be bigger than this number because turbulent flow, all of the things being equal, should give a higher heat transfer coefficient and hence higher heat transfer than laminar flow for the same temperature gradient. So that checks out, and these solutions check with what's in the book. By the way, I should mention, all of these problems I took from the book. They were potential homework problems, and I chose not to give them to you as homework. I'm just solving them for you so you can see a couple of examples of how this is done. Okay. Example number 2. We have this, by the way, is like the classic heat transfer problem, right? You see this all the time in, like, heat transfer exams. I think I even asked this in a fluids exam one time, the fluids portion of it, final exam in my class maybe a year ago. Okay, so we have a long, thin metal plate of width 0.2 meters, vertical dimension 3 meters, and an initial temperature of 593.15 Kelvin. It's hung vertically after some sort of heat treating process, right? So here's the image. Here it is. It's hung vertically. The width is 0.5, right? So the flow is moving in that direction. And then the vertical dimension is 3 meters, right? So it's hung vertically. That's the vertical dimension. So this is like a short plate that's like tall, short, tall plate. Thin, short, tall plate. Yeah. Okay. All right. So we're asked to determine the initial rate of heat loss if the air is flowing. Heat loss if the air is parallel to the flow. If the air is parallel to the flow. Huh. I think what is meant here is the plate is parallel to the flow. If the plate is parallel to the flow. Yeah. Let me I think that's the wording that came right from the book, and it's a little confusing, so I'll fix that. Right, basically this configuration, right? The plate is parallel to the flow. Okay. Account for heat loss from both surfaces, right? So the surface that we're looking at, and then the one on the far side that's hidden from us. Determine the initial rate of heat loss if the plate is turned so that the width is perpendicular to the airflow, right? So I'm just turning the plate 90 degrees. So now this width is into the page. And so now the air is blowing not over something that's flat and thin, but something that's a little bit wide. Account for heat loss from both the front surface and the back surface of the plate. So front surface, back surface of the plate. Which orientation maximizes the initial cooling rate? Okay. I will, before we jump into this, just give you one caveat here, which is you guys are now equipped, given what we've talked about in this lecture, to solve this part of the problem. You do not yet have enough information to solve this part of the problem, because this part of the problem is in chapter 6, which is flow over cylinders, spheres, and cylindrical-like objects. It turns out that this correlation is given in chapter 6, even though it kind of belongs in chapter 7, but it's not in chapter 7, it's chapter 6. So I'll show you guys how to solve this using chapter 6. And then once you guys see the chapter 6 lecture, it'll probably make more sense, but it'll make sense anyway, because it's not too bad. Okay, so we're going to make our typical assumptions. So steady state conditions. We're going to neglect radiation, right? Remembering that this is a heat treating process, right? So the initial temperature of the plate is well above ambient temperature, so we might worry about radiation. We don't in this problem. We assume that it's negligible, and our properties are going to be assumed to be constant. Okay, so let's solve this one first, which is the one that we are equipped to solve. All right, we're going to go through our 10-step process, right? We are going to repeat silently to ourselves that all action is in the boundary layer, right? Because that we're solving for heat transfer in the boundary layer, right? Just as a reminder. Okay, we're going to identify the flow geometry. This is flow over a flat plate, so no worries there. We're going to specify the reference temperature, skipping step 4, which is for mass transfer, and evaluate pertinent fluid properties at that temperature, right? So we need a film temperature. The plate itself starts at 593, and the free stream is at 303 Kelvin. We add those together, divide by 2, we get our film temperature of 448.15 Kelvin. I want to mention a subtlety here, which is we're asked to determine the initial rate of heat loss, initial rate of heat loss, right? So this could become a very ugly transient problem. That word initial signals that all we care about is the heat transfer at the initial time when the plate is initially exposed to 303.15 Kelvin. So do not feel the need to jump into BO numbers and Fourier numbers and all that insanity from chapter 5. All we're doing is solving for the initial heat transfer, right? So just that first moment. So no time dependency here at all, at least not for this problem the way that it's phrased. You could imagine an awesome problem that would include all of this and like transient like heat transfer conductivity inside the plate, right? It's probably lumped capacitance, so probably not too hard. But you can imagine such a problem. Maybe that will be a future quiz for a future class. But we're at the end, so we can't do it now. Anyway, okay, so I've got my film temperature of 448 Kelvin. Same deal as before, right? Back in my day, we would have looked up this value in a table or interpolated between two entries in a table because this is a non-standard value. You guys have AI, so you could just ask AI what the value is. But again, make sure that you are checking your values against something that is a verifiable source of truth, right? So either a table in a textbook or a lookup table in some sort of verified computer program or something like that. Do not trust AI with these values because it will mess it up. It will hallucinate and you will spend an enormous amount of time solving the wrong problem. So we're looking for thermal conductivity, viscosity, and Prandtl number at about 450 Kelvin. So here's my table from the book, 450 Kelvin. Yep, thermal conductivity, right? 37, right? 38 here, right? Notice the difference is 10 to the third, right? So these are actually the same number, just 1,000 off because the book for some reason wants to multiply everything by 10 to the third. Don't know why. So those numbers are good. Viscosity, 315. Right. Okay. About 320, 324. Right. So those are very similar. Again, the difference here is because the book is multiplying by 10 to the minus 6. I'm just giving you the number with the exponent built in. And then Prandtl number, 0.662. 0.686. That's a little far off. But not too bad, not too bad. So I'm going to go with this number, even though it's a little bit off. This might be something that's far enough off that if I were not just solving an example problem in a lecture, I might actually go to a third reference and actually check to see if I can figure out which one of these is right, because this is a bit far off, right? It's like this is the Prandtl number that's associated with. It would be like way down here, right? The number is dropping, so it'd be like a much higher temperature. But I asked AI a bunch of times, and it's like, yep, that's the Prandtl number. So we'll go with that, right? Even though it's probably not right because it's more like 0.68. Anyway, okay, we're going to use this value. All right. So we're going to calculate the Reynolds number, and then we're going to determine whether the flow is laminar or turbulent. So in this case, we have 4 meters per second is the upstream velocity. X is the full width of the plate. Full width of the plate, 0.2 meters. Yep. So we're looking at the Reynolds number at the edge of the plate, the back edge of the plate, because we're interested in an average heat transfer coefficient over the whole plate. And then here's the viscosity that we got from before. So 25,000, right? 397 is what I get. That is less than 5 times 10 to the 5th. So this is laminar flow. All right. So knowing that we have a laminar Reynolds number, we have flow over flat plate, we are going to choose the Nusselt number correlation associated with an average over the entire surface, right? So average determines heat transfer rate for the entire surface. That's what we want because we're interested in initial heat rate for the whole plate. Okay. So we're going to choose the appropriate Nusselt number correlation for that combination of conditions, flow over a flat plate, laminar Reynolds number, averaged over the plate. And we're going to plug in our parameters and solve for a heat transfer coefficient. Then once we get the heat transfer coefficient, we're going to plug that into Newton's law of cooling, and we're going to get the amount of heat that this thing is dissipating into the free stream flow at the initial moment, right? Because it's not a transient problem, because we weren't asked for any time other than the initial time. All right, here is my appropriate Nusselt number correlation for laminar flow over a flat plate average value. I got to check to make sure that the Prandtl number is greater than 0.6, which is where this applies. Yes, it is 0.662 or 0.686, depending on who you believe. So here I am just plugging in the numbers, right? So I've solved for HL, plugging in the numbers. Here's my Reynolds number. Here's my Prandtl number, 662. Here is my my K value. Here's my L value. And what I get is 17.66. Okay, so 17.66 watts per meter squared Kelvin. That's my average forced convection heat transfer coefficient. I'm going to plug that into Newton's law of cooling, plug in my area, my temperature difference, and get a value. I am multiplying by 2 because I'm specifically told in the problem account for heat loss from both surfaces, right? So I calculated the heat loss from one surface, and multiplying by 2 gives me the heat loss from the other surface. They're identical, mirror images of each other, right? So I get the value for 1, multiply by 2, and that gives me the total. Here's my H value. Here is my height of my plate, my width of my plate, and then temperature difference. I get 6.1 kilowatts, 6,146 watts. This checks with the book pretty well. So I'm going to go with that as my answer for the first part. For the second part, you guys have not yet seen this. If you're looking at this, watching this video in summer 2026, this is chapter 6 stuff. But this is basically flow over, it's cross flow over a cylinder. In this case, our cylinder happens to be a thin plate perpendicular to the flow. There is a Nusselt number correlation for that, which happens to have the exact same form as all the Nusselt number correlations that we've talked about already. The only difference is that C and M are different, right? So this should feel and look very familiar. It's exactly what we talked about in this lecture, with the exception of a need to find C and M empirically, which we also talked about in this lecture. So our flow geometry is non-circular cylinder, which is what this table represents from chapter 6. We're going to calculate the Reynolds number, determine whether the flow is laminar or turbulent, decide whether we need an average or a local Nusselt number, pick the right correlation, and solve and plug in the parameters. Okay, so it turns out that for a thin flat plate perpendicular to the flow, the Reynolds number, I should say Reynolds number sub D here. Reynolds number is based on width, right? And the width is this, right, which is the value that's given. And it turns out that that width is the same width as what's given in the problem. So the Reynolds number is exactly the same as it was before, right? No changes. And then the equation for non-circular cylinders in gas crossflow is that same Nusselt number correlation, except we need C and M. So it turns out that we have a table that gives us, for a range of Nusselt numbers, the C value and the M value. Our Nusselt number is 25,000. It falls right in this range for the front, and it also falls in this range for the back. And so we can now calculate the Nusselt number for the front and the back just by pulling the appropriate C and M for the front and the appropriate C and M for the back. Okay, so that's what we're going to do. All right, so we've just selected the appropriate Nusselt number, and now we're plugging in parameters, right? So here I am solving my Nusselt number for the forced convective heat transfer coefficient for the front. That's sub F is front, sub B is for back. Notice that I'm using H bar, so an average value over the entire diameter D. So so Nusselt number sub D is equal to, multiplied by K over D gives me that coefficient. Here is me plugging in, right, C and M, right? C is 0.667, M is 0.5, 0.667, 0.5, right? Plugging in, right? And then here's my K over D, and out pops forced convection heat transfer coefficient for the front side of the plate of 17.74 watts per meter squared Kelvin. Here it is for the back, right? Same equation except C and M change, right? So C here is 0.191 and C here is 0.667. 0.191, 0.667. Everything else is the same, plugging in, plugging in, plugging in. And this was actually surprising to me. I had to check this. The back of the plate ends up having a higher forced convection heat transfer coefficient than the front of the plate, right? That seems very weird to me, right? Because like the fluid actually has to like wrap around the back in order to get there, in order to take heat off the back. But it's right. So it probably has something to do with vortex shedding, right? And the vortices basically like the flow is laminar, right? So right, you can actually see it here, right? Kind of represented. It probably has something to do with a turbulent eddy that gets formed here, and actually puts a little bit of a turbulent convection boundary like on the backside of the plate. That's my guess for why the value is higher. That was weird and surprising to me, but anyway, it checks out with what the book says. So we'll go with it. Okay, and then here I am just adding up, right? So the total heat transfer from the plate in this configuration is the heat transfer from the front side plus the heat transfer from the back side. Those areas are the same, the temperature differences are the same, and so I just get to combine those two front and back heat transfer coefficients together like this, right? That's the distributive law of multiplication, right? So just doing that to make my math easier, plugging in the numbers, and out pops 7,894 watts, which matches with what the book says. And so the end result is that for the plate in the parallel configuration, we've got 6,146 watts of cooling. And for the plate in the perpendicular configuration, we've got 7,894 watts of cooling. So if you're interested in maximizing the cooling of this plate at the initial time, this is actually the better configuration. This was surprising to me. But that's the result. So pretty interesting. Okay, so we've got that one figured out. Let's do a third example. This is the last one. This, by the way, is a mass transfer example. So we've done two heat transfer examples. I wanted to show you a mass transfer example to show you how the mass transfer equations work. This one will be near and dear to your hearts if you're taking the class in summer 2026. You basically already solved a problem like this when we were talking about cooling towers at the J.R. Kelly generating station at GRU, right? The power plant. You guys actually designed a condenser, and some of you were worried about makeup water and how much makeup water you would need and how much evaporation you would get. And this is that exact problem, right? So this is why I picked this, because this should be familiar to you guys if you're taking the class in summer. So we have a reservoir of condensing cooling water used in a power plant, right? Stored in a pond that is 1,000 meters long and 500 meters wide. Due to evaporative losses, it's necessary to periodically add makeup water to the pond to maintain a suitable water level, right? So water is evaporating from this pond, and we're pouring water back into the pond to make sure that the pond stays at a particular height, right? Probably a height above like an inlet valve or something like that, or an inlet conduit for the power station. So we're going to make some assumptions given to us by the book. One is isothermal conditions at about 300 Kelvin for the water and the air. Two is free stream air is dry and moving at a velocity of 2 meters per second in the direction of the 1,000-meter pond length, right? So as drawn here, right, the fluid is air. It is dry, right? So 0% relative humidity, and it's blowing in the long direction, the 1,000-meter direction over this cooling pond. And the boundary layer on the water surface is everywhere turbulent, right? So that's an important piece of information. The fluid is basically tripped to turbulence somehow at the leading edge of this pond. And so we're going to end up using like turbulent correlations for the entire length of the pond, not a laminar to turbulent transition. Okay, so we're asked to determine the amount of makeup water in kilograms per day that should be added to the pond daily. Yeah, there we go. Okay, so a couple of initial assumptions. This thing is operating situations in steady state, and all of our properties are constant. Um, that same set of 10 steps is going to apply to mass transfer problems as it applied to heat transfer problems. So we are going to say quietly to ourselves, all action is in the boundary layer. Just to remember that we are solving for now a um, concentration boundary layer, right? So we're looking at mass transfer instead of heat transfer, but everything that's happening is happening inside the boundary layer. So that's what we're solving. We're going to identify the flow geometry. This is effectively flow over flat plate, right? It's basically a pool of water. The water is flat. So this from a heat transfer, mass transfer perspective is just going to look like a flat plate. Specify the reference temperature. This is where we invoke step 4. We've skipped this every other time because we've only solved heat transfer problems. For mass transfer, um, we're going to use the temperature at species B, right, which we are specifically told isothermal conditions for the water and the air, 300 Kelvin, right? So that's what we're going to use because species B is the air. Water is diffusing air, which is species A. Air is species B, which is where the water is diffusing into. So 300 Kelvin. Okay, we're going to evaluate pertinent fluid properties at that temperature. So at 300 Kelvin, which happily shows up in almost every table, we're going to calculate properties. So we need properties both for the um, water vapor and for the air. So for the air at 300 Kelvin, I have a thermal conductivity, which here it is, right? 26.3. I have a viscosity of 15.96 times 10 to the minus 6, right? So that's there. And I have a Prandtl number of 0.707. I did not need to ask AI for these numbers because 300 Kelvin is right in the table, right? I'm going to just ignore the 0.15 Kelvin temperature difference and I'm going to pull the numbers right out of the table. Okay. We also have to evaluate how much water vapor is in the air once the air gets saturated. And so for that, we have to go to the saturated water tables for thermophysical properties. So at 300 Kelvin, the specific volume for air, no, blah, blah, sorry, specific volume for water, and this is water vapor, right? Not water liquid, water vapor at 1 atmosphere and 300 Kelvin is 39.13 cubic meters per kilogram. That's just 1 over the species concentration, 1 over the density, right? So I'm going to take 1 over the specific volume, 1 over 39.13, and that's going to give me 0.256 kilograms per cubic meter. So that's now the species concentration. It has units of density, species concentration in the air once the air gets saturated. Okay. And then I need a diffusion coefficient, right? Because I'm now talking about Sherwood number correlations. Sherwood number correlations have diffusion coefficients and Schmidt numbers. So in the book, we have substance A, water, diffusing through substance B, air at about 300 Kelvin, right? 298. And that diffusion coefficient is about 0.26 times 10 to the minus 4. So that's where I get this value. These all come from tables. I guess if you wanted to have AI look them up, you could, but why bother? It's 300 Kelvin, right? Just look them up in tables. We are going to need a Schmidt number because we're going to have a Sherwood number correlation. So the Schmidt number, remember, is the viscosity divided by the diffusion coefficient. Here's the viscosity. Here's the diffusion coefficient. Works out to be 0.61. All right. I've got all of my parameters calculated. Now I need to find the Reynolds number, determine whether the flow is laminar or turbulent, decide whether I want a local or a surface average mass transfer correlation, and then pick the appropriate correlation. Okay, here I am calculating a Reynolds number. The flow was 2 meters per second, right? Yeah, 2 meters per second. The length of the total pool is 1,000 meters. The viscosity was given before 15.89 times 10 to the minus 6 square meters per second. And so I get a Reynolds number of 1.26 times 10 to the 8th. That exceeds 5 times 10 to the 5th. So this is turbulent flow. And interestingly, remember, we were actually told that the flow is trip to turbulence. Where is that? Yeah, turbulent everywhere, right? Boundary layer on the water is turbulent everywhere. So we knew that the flow was turbulent from the get-go, right? So I've already circled turbulent here even before calculating the Reynolds number. But We need the Reynolds number to plug into the Sherwood number correlation. Okay, so there's the Reynolds number. Um, I'm looking for the entire mass transfer by evaporation from the pool. So I need an average Sherwood number. So I'm going to pull my average Sherwood number correlation. This is the one. Remember. Let's go back. Where is it? That's this one, right? So my Sherwood number correlation that has both the laminar and the turbulent components. Remember, for a completely turbulent boundary layer, one where we trip to turbulence right at the beginning, A is equal to 0. So A is equal to 0 for this correlation. So if I go back to my problem, right, for completely turbulent boundary layer, A is equal to 0. So I'm using this correlation, but A I don't need to worry about. And so all I've got then is this first part of it multiplied by the Schmidt number to the 1/3 power. I do need to check to make sure that the Schmidt number is between 0.6 and 60. It's 0.61, so I'm in good shape there. And then here's the correlation, right? So this is just this rewritten without the A in it, right? Because A equals 0. And I want to find this mass transfer coefficient, this average mass transfer coefficient for the entire body of water. So I'm going to rearrange this to solve for H. So H is equal to the Sherwood number. This K, this K should be a diffusion coefficient. This should be DAB. Okay, right. It shows up here, but I forgot to change it here. Okay, so I'll change that. This should be DAB. All right, so here is my convection coefficient, Sherwood number times not K, but DAB divided by L gets me this. And here I am just plugging in values, right? 0.37, Reynolds number to the 5/4, 4/5, Schmidt number to the 1/3. Here is my diffusion coefficient. Here's my L, and what I get is 0.00246. Notice the units. It's meters squared, so it has units of velocity, kind of a weird unit for mass transfer coefficient, but that's what it is because it ends up getting multiplied by a species concentration, right? So the units work out fine, but this is not meters squared per second. It's meters per second. Okay, and now I have everything I need, right? So I'm going to solve for the the mass transfer coefficient, which I actually did in the previous slide. And then I'm going to solve for the rate of water evaporation. So here's the equation, right? It mirrors Newton's law of cooling. The rate of evaporation, right? So mass per time is equal to that mass transfer coefficient, that average mass transfer coefficient times the total exposed area multiplied by the species concentration of water at the surface of the water, right? And you should have learned in thermo, I hope you remember from thermo, that if you have like a liquid surface, the relative humidity at that surface is 100% relative humidity. That's why when it rains, the humidity is 100% because there's water in the air. So this is why we calculated the species concentration for saturation conditions here, right? So that is actually the concentration of water vapor in air at this spot right above the pool, and then far away from the pool, right outside of the boundary layer, the edge of the boundary layer, we've got the relative humidity times whatever the concentration happens to be, but we're told that the relative humidity is 0, right? So this whole term is 0, right? I think pond evaporation, makeup water, everywhere turbulent, free stream air is dry, right? Dry, which implies relative humidity is equal to 0. So that's where that comes from. That's why this is 0. Okay, so now I'm just plugging in numbers, right? So here's my mass transfer coefficient. Here's my area, length times width. Here's my saturation species concentration right near the liquid water surface. Here is in the free stream, my concentration of water vapor, which is 0. Plug all that in and I get 31.53 kilograms per second. That seems like an awful lot, right? But remember, this pool of water is 1,000 meters long, right? It's a kilometer long and it's half a kilometer wide. This is a big lake, right? So not so surprising that this number is as large as it is. Um, so to figure out how much water we have to add, we just have to convert this from kilograms per second into kilograms per day, right? Because that, remember, is what we were asked to solve for, right? Kilograms per day that should be added to the pond daily. Um, Okay, so here it is. I'm just taking my 31,053, multiplying by the number of seconds in an hour, 24 hours in a day, and that gets me 2.724 times 10 to the 6 kilograms per day of water, right? It's a big amount of water, but not surprising for something the scale of a power plant, which you guys are familiar with because we've solved those kinds of problems already as the challenge problems in this class. And it turns out this number checks with the book. Again, this is a problem borrowed from the book that was going to be a homework problem, but I wanted to solve it for you in this lecture because it's relevant to the power plant stuff that you guys have already been thinking about. Okay. Whoa. That was a lot. And that was only like the first like 3 sections of this chapter. So if you're still here and still listening, I really appreciate your time and attention. Um, Hopefully there'll be maybe one more of these if we've got time, but that's it for this particular lecture. So I got to get my mouse back. Oh, there we go. Okay, so we'll wrap it up there. Thanks for your time, and we'll see you around. Okay, bye.